Billions of chips, insane machines, and more seasoning than you thought legally possible. This is how Doritos are really made. Behind those iconic triangles is a non-stop industrial process powered by heat, pressure, and flavor engineering on a massive scale. In this video, we're taking you inside the factory to see the wild reality behind how Doritos chips are made. The manufacturing journey of Doritos begins long before the chips ever hit the fryer or the seasoning drums. It starts in the cornfields. Doritos use a specific variety of whole kernel yellow corn selected for its starch content, moisture levels, and particle uniformity after grinding. The corn is harvested at peak maturity and tested for aflatoxins, foreign material, and protein content before it's even accepted at the plant. Only corn that passes this first round of quality standards is brought in for processing. At the factory, truckloads of bulk corn arrive daily and are funneled into underground receiving pits that use gravity to guide the kernels onto conveyor belts. These conveyors feed the kernels into the first stage of preparation, the cleaning and sorting system. In this system, the corn passes through an array of vibrating sieves, rotating drum sifters, and powerful pneumatic air classifiers. Large debris like cobs, sticks, or stones are removed first. Then, finer contaminants like dust and small broken kernels are extracted using aspirators that draw away lightweight particles. Magnetized rollers also scan the corn flow to remove any traces of ferrous metal, ensuring total cleanliness before cooking. Once cleaned, the corn moves into the Nixtamalization phase, a crucial and traditional process that transforms the flavor, texture, and nutritional properties of the corn. Nixtamalization involves cooking the whole kernels in a large stainless steel vat of hot water mixed with food-grade calcium hydroxide, also known as slaked lime. The corn is cooked at around 85 to 90 degrees Celsius for approximately 20 to 40 minutes, depending on the batch size and corn variety. This lime water solution serves several purposes. It breaks down the outer pericarp of the kernel, making it easier to grind and digest. It also increases the bioavailability of niacin, softens the internal structure of the corn, and imparts the distinctive flavor profile that Doritos are known for. After cooking, the corn is not immediately processed but left to soak, usually for 8 to 12 hours in the same solution. This extended soaking allows the lime to fully penetrate the kernel and continues the softening and flavor-enhancing process. After the soaking phase, the corn is drained and rinsed thoroughly in large industrial washers that spray it with jets of clean water while gently tumbling the kernels. The goal is to remove the loosened pericarp, excess lime, and any residual cooking liquid. What remains is called nixtamal, a soft, pliable corn mass that still holds the shape of whole kernels, but has a meaty, hydrated texture. The nixtamal is now ready to be ground into masa, the dough-like base of every Dorito chip. The grinding is performed using industrial stone mills, rotating horizontal stones made of volcanic rock or synthetic composites, precisely aligned to maintain a consistent grind size. The nixtamal is fed between the stones, and the pressure shears the softened corn into a dense, cohesive paste. This paste is the masa, and its texture is critical. It needs to be soft enough to press, but dry enough to hold shape without sticking. Operators continuously monitor the temperature of the mesa during grinding. Too much friction can overheat the dough, which affects the final chip texture. Ideal mesa temperature coming off the stones is around 45 to 55 degrees Celsius. Viscosity is checked using inline sensors that measure flow resistance, and if adjustments are needed, small amounts of water or returned dry mesa are mixed back in using an automated feedback loop. Now, it's time to form the masa into flat sheets. The ground mesa is transported via auger screws into a sheeting machine, which extrudes the dough between two polished stainless steel rollers. These rollers are adjustable to control sheet thickness down to the millimeter, usually targeting between 1.2 and 1.8 mm, depending on the final chip specification. The mesa sheets are laid directly onto a continuously moving conveyor belt that carries them to the cutting station. The cutting system is a rotary die cutter, a high-speed drum outfitted with rows of equidistant triangular blades, each perfectly matched to the iconic Doritos shape. As the mesa sheet moves beneath the drum, the rotating blades stamp out thousands of identical triangle chips per minute. Each cut is sharp and precise, with just enough spacing to leave minimal waste dough between cuts. The trimmings, the thin slivers of masa between triangles, are not discarded. They are automatically lifted via vacuum collection and returned to the start of the sheeting process. These scraps are reincorporated into the fresh dough, ensuring efficient use of material and maintaining consistency. The cut triangle chips now move on a flat conveyor to a brief baking phase, which we'll explore in detail in the next section. This preliminary baking is vital to reduce moisture and stabilize the chip before it enters the high heat frying zone. But before any oil is introduced or seasonings are applied, this early stage, cleaning, nixtamalization, grinding, sheeting, and cutting, is where the foundation of Doritos' crunch, shape, and flavor truly begins. Once the precisely cut mesa triangles are formed and conveyed forward, they reach one of the most critical transitions in the Doritos factory, the pre-baking zone. Though often overlooked, this short but essential phase serves as a structural stabilizer that prepares each chip for frying without deforming, bubbling uncontrollably, or becoming overly saturated with oil. This stage controls the internal moisture content and builds the texture foundation that will result in the signature crunch. The masa triangles, still soft and slightly tacky from the sheeting process, move onto a continuous metal mesh conveyor belt that leads directly into an industrial tunnel oven. This pre-bake oven is not designed to fully cook or brown the chip. Instead, its primary goal is to reduce the moisture level from roughly 50% down to about 25 to 30%. This ensures the surface of the chip becomes firm enough to hold its shape when exposed to hot oil, but not so dry that it resists expansion. The oven itself is typically divided into multiple thermal zones. The first zone begins around 160 degrees Celsius, gradually increasing to about 260 degrees Celsius by the final section. Heated air is circulated by high-velocity blowers, creating a turbulent flow across the top and bottom of the chips to ensure uniform dehydration. The baking conveyor is made of stainless steel mesh that allows hot air to penetrate from below, guaranteeing that no side of the chip is undercooked. Sensors monitor humidity at various checkpoints, and real-time data is fed into the oven's PLC system to dynamically adjust airspeed and temperature depending on fluctuations in mesa density, ambient humidity, or line speed. As the chips exit the oven, they emerge firmer, drier, and more resilient, yet still pale in color and lacking the blistered surface texture that defines a finished Dorito. That transformation happens in the next stage, the continuous fryer system. Here, the par-baked chips fall gently off the oven belt and descend onto the infeed section of a massive open surface fryer. The fryer itself is a high-capacity stainless steel vessel filled with continuously filtered cooking oil. Most Doritos production lines use either corn oil, sunflower oil, or a proprietary blend of vegetable oils chosen for their high smoke points and neutral flavor profiles. The oil is maintained at a stable frying temperature of approximately 180 degrees Celsius, with variations of only +2 GC allowed during operation. Chips are submerged in the oil for about 35 to 55 seconds, depending on their exact moisture level and thickness. The chips ride through the fryer on a submersion conveyor, essentially a mesh belt with downward pressure bars that keep the chips fully immersed while preventing stacking or overlap. This is crucial because the frying process is not just about dehydration, it's about vaporization. As the residual water inside each chip turns to steam, it forces itself outward, puffing the chip slightly and creating those micro blisters and bubbly textures on the surface. This internal steam pressure is carefully managed. Too little and the chip stays flat and hard. Too much and it balloons into a hollow pocket. Above the fryer, exhaust hoods pull away steam and vaporized oil particles, filtering them through a heat recovery system that can reuse waste heat to pre-warm incoming oil. This system conserves energy and helps maintain a cleaner frying environment. The oil itself is constantly recirculated through centrifugal filters and fine mesh screens to remove crumbs, starch residues, or burnt particles. Fresh oil is added in controlled volumes throughout the day to maintain chemical balance and replenish lost volume. Once fried to the optimal light golden color, the chips are lifted from the oil by an outfeed conveyor and immediately pass through a vertical de-oiling section. Here, powerful centrifugal blowers aimed at precise angles blast away excess surface oil. This keeps the chips crispy, prevents pooling in the packaging stage, and ensures that the seasoning will stick without creating grease buildup. The chips then pass through an ambient cooling tunnel to bring them quickly down to room temperature. Cooling is not merely for worker safety, it stabilizes the fat within the chip and prevents condensation when entering the seasoning drums. Now comes one of the most defining stages of the entire process: seasoning application. Each Dorito must carry the bold, vibrant flavor profile it's known for, whether that's nacho cheese, Cool Ranch, spicy sweet chili, or any of the dozens of global variants. The seasoning powder itself is a proprietary blend of flavorings, including real cheese powders, spices, salt, sugar, yeast extract, and encapsulated flavor oils that deliver controlled release bursts of taste. The chips are conveyed into a rotating seasoning drum, an inclined, slowly turning cylinder lined with food-grade stainless steel. As the chips tumble over one another, a dry powder dosing system mounted above the drum applies the seasoning using precision augers and dispersing nozzles. These nozzles can spray a uniform mist of oil if needed before the seasoning hits, which enhances adhesion for certain formulations. The rotation speed of the drum, the flow rate of the powder, and the incline of the system are all adjustable and carefully tuned. Too slow, and the powder won't distribute evenly. Too fast, and the chips may break, or the powder may collect unevenly on some sides. Optical sensors track the color and surface reflectivity of the chips as they exit the drum. If the reflectivity is too high, that could indicate under-seasoning. If it drops below a preset threshold, over-seasoning may be occurring. This live data is fed back into the controller, which tweaks the feed auger speed or pauses the oil spray accordingly. The seasoning drum is one of the most customized parts of the Doritos line. Different flavors use different particle sizes, densities, and oil volumes, which means the drum design and spray system must adapt depending on the product. Some drums include vibrating baffles or spiral lifts that increase tumbling action for extra thick chips or extra coarse seasoning. Once seasoned, the chips are directed into the weighing and bagging system, but before that, they undergo an automated inspection phase. High-speed vision cameras scan every chip for size, shape, and color. Broken chips, overly curled pieces, or visibly under-seasoned chips are removed via air-jet rejectors. These rejected chips are collected and sent either for regrinding or biomass energy use. Only chips that pass inspection enter the multi-head weighers, machines equipped with a dozen or more radial weighing hoppers. These hoppers constantly drop chips into a central collection bucket when the combined weight equals the target for each bag, typically between 28 g and 198 g, depending on package size. Once a precise combination is reached, the chips are dropped into a vertical form-fill-seal bagging machine. Here, continuous rolls of metallized polypropylene film are formed into tubes, sealed along the sides, and crimped at the bottom. The The weighed chips are dropped into the formed bag tube just before the top is sealed and cut. Each bag is nitrogen flushed to displace oxygen, extending the product's shelf life and preserving crunch. Then, the bags are labeled, batch coded, and passed through a final metal detector before being boxed for palletization. After the freshly seasoned Doritos chips are individually weighed, bagged, sealed, and inspected, the production line moves into the critical post-packaging and logistics phase, where efficiency and traceability become as important as taste and texture. Though the chips are now fully formed and flavor complete, the operation is far from over. In fact, from a manufacturing systems perspective, the next stages, palletization, storage, shipping, and quality verification, are just as sophisticated and optimized as any in the earlier production line. The newly filled Doritos bags exit the form fill seal machines onto a series of conveyor belts designed to collect, orient, and organize them by SKU, bag size, and flavor variant. These conveyor lines merge into case packing stations, which use robotic arms equipped with vacuum suction grippers or gentle mechanical paddles to lift and place the chip bags into cardboard cartons. These boxes are pre-folded, glued, and printed with relevant product information, including product code, flavor, best before date, factory location, and a scannable QR or barcode that links to all production details. Each carton is inspected for weight and shape before it moves to the next phase. Even slight deviations in shape, caused by mispacked bags or an uneven number of chips, can disrupt downstream palletizing operations, so edge integrity and sealing quality are monitored automatically using high-resolution 3D scanning systems. Any carton that fails to meet dimensional tolerance is rejected from the main flow and rerouted for manual inspection or reboxing. Once cleared, the filled cartons are transferred to automated palletizing stations. In most modern Doritos factories, this process is entirely robotic. A multi-axis robotic arm lifts groups of cartons and stacks them onto wooden or composite pallets according to a predefined stacking pattern optimized for shipping efficiency and stability. These patterns are determined by a logistics algorithm that accounts for box dimensions, weight distribution, and the pallet's ultimate destination, whether that's a domestic warehouse or a long-haul overseas container. After each pallet is completed, a robotic stretch wrapper encircles it with several layers of clear plastic film to stabilize the load. A printed pallet ID label is affixed, containing detailed information about its contents, including product types, quantities, batch numbers, and destination. These labels are scanned into the warehouse management system, linking each pallet to the larger production database in real time. From here, pallets are routed into the warehouse zone. Doritos production facilities feature climate-controlled warehouses designed to maintain product quality throughout the storage period before distribution. These zones are not refrigerated, as Doritos are shelf-stable, but they are meticulously managed to avoid conditions that could lead to staleness or packaging deformation. Temperatures are generally held between 18-22 degrees Celsius, and humidity is controlled below 50% to prevent foil bags from absorbing moisture or warping. Inventory in the warehouse is managed by automated storage and retrieval systems. Tall racking structures are navigated by robotic cranes that pick and place pallets based on real-time demand, stock rotation policies, and shipping schedules. Each pallet's position in the warehouse is logged down to the specific shelf and column level, making retrieval highly efficient. The warehouse management system is integrated with the factory's enterprise resource planning software, ensuring that production and distribution are fully synchronized. While in storage, every pallet of Doritos is subject to randomized quality control sampling. A team of trained technicians removes sample bags from various pallets across shifts and production lines and sends them to a separate sensory evaluation lab within the facility. Here, samples undergo a series of tests. mechanical compression for bag integrity, gas analysis for nitrogen content, and oxygen intrusion, seasoning density checks, and most importantly, taste and crunch testing. Crunch is measured using a texture analyzer, a machine that applies controlled force to the chip and records resistance, fracture point, and acoustic feedback. The results are compared to golden standard reference chips to determine if the texture profile remains within acceptable limits. Seasoning adhesion and intensity are tested via flavor profile mapping, and every element from saltiness to umami to residual aftertaste is scored and compared against target values. If a trend of inconsistency is detected, an investigation is initiated, often leading to a review of upstream production parameters like fry temperature variability, seasoning drum throughput, or even ingredient batch variations. This closed-loop system helps prevent long-term quality drift and enables real-time course correction. Beyond the factory, the logistics infrastructure that gets Doritos from warehouse to retail shelves is another marvel of scale and precision. The factory works in tandem with PepsiCo's broader distribution network, which includes regional distribution centers, cross-dock terminals, and last-mile delivery nodes. Based on retail demand forecasts drawn from sales data, seasonal trends, and real-time POS metrics, shipment volumes are adjusted dynamically. This avoids overproduction and waste while ensuring retailers remain stocked. Each shipment of Doritos is accompanied by a digital bill of materials, which includes all traceability data from ingredient sourcing to packaging and palletization. This document allows not only for internal tracking, but also rapid action in the event of any product recall or customer complaint. If an issue is raised about a particular bag, say under-seasoning in a certain region, operators can trace the issue back to a specific lot, machine, shift, and even the original corn batch used in production. Globally, the manufacturing process for Doritos is also adapted based on regional consumer preferences and regulatory standards. While the foundational steps remain consistent, nixtamalization, sheeting, cutting, frying, and seasoning, the recipes and specifications can vary significantly. For example, in the US, cheese-based seasonings often use cheddar powder and lactic acid for tang, while in the UK or India, formulations may include less salt or alternative flavor enhancers to meet local guidelines or taste expectations. In markets like Japan or South Korea, where flavor sophistication and novelty are highly valued, factories produce limited edition Doritos featuring ingredients like wasabi, squid ink, or yuzu citrus. These variations often require changes in seasoning particle size, oil stability, or packaging material. And as such, the production lines must remain flexible. To facilitate this, Doritos factories use modular flavor dosing systems and quick changeover machines that allow seamless transitions between variants with minimal downtime. In addition to this flexibility, Doritos production lines are increasingly being outfitted with smart factory technologies. These include IoT sensors, predictive maintenance platforms, and AI-driven scheduling software. For instance, a vibration sensor might detect a subtle change in the seasoning drum's motor function that suggests a bearing is beginning to fail. Rather than waiting for a breakdown, the system automatically schedules maintenance during a planned production lull, avoiding unplanned downtime. Energy efficiency is also a growing focus. Waste heat from the fryers is often recovered through heat exchangers and used to preheat water for the nixtamalization tanks or warm the air in the seasoning room. Air filtration systems recycle hot air from the fryer exhaust into the building's HVAC to reduce natural gas usage. These sustainability practices help reduce both costs and environmental impact. Waste reduction is another area of innovation. Trimmings from mesa sheeting, broken chips, and seasoning dust are no longer treated as loss. Instead, they're collected, analyzed, and often reused in animal feed production, compost systems, or converted into biofuel at third-party processing facilities. Factory waste targets are set annually, and each production shift is scored on both yield efficiency and environmental impact. Ultimately, the journey of a Dorito from corn kernel to crunchy triangle is one of constant refinement. At every stage, whether it's dough hydration, fryer calibration, seasoning density, or robotic case packing, the process is governed by a matrix of mechanical precision and human sensory experience. The chips may seem simple to the average consumer, but behind every bag lies a production system that blends food science, industrial engineering, supply chain logistics, and consumer psychology into one unmistakable result: bold flavor, addictive crunch, and global brand consistency. It all starts with the consumer insight team, which continuously analyzes sales data, social media trends, cultural food movements, and even fine dining innovation to identify gaps or opportunities in the market. A spike in interest around birria tacos, for example, might inspire a spicy beef consommé Doritos concept. Once a viable trend is spotted, food scientists and flavor chemists work alongside marketing strategists to develop flavor direction briefs, detailed documents that outline the intended taste profile, emotional positioning, and target audience. In PepsiCo's Flavor Innovation Centers, teams begin with flavor mapping. This involves breaking down target flavors into their basic aromatic and taste components. For a concept like Flamin' Hot Dill Pickle, the scientists would analyze heat components, acidity, herbal notes, and salt balance. Using GCMS, flavor chemists extract and replicate aromatic profiles to ensure they match real-life foods as closely as possible. Next, benchtop seasoning blends are created in small batches using food-grade flavor powders, encapsulated oils, anti-caking agents, and natural extracts. These are applied to test chips using miniature tumblers that mimic the behavior of full-scale seasoning drums. Each test batch is evaluated by sensory panels, trained tasters who assess flavor intensity, balance, aftertaste, aroma, and how the flavor interacts with the chip's natural corn and oil base. Their feedback is mapped against a flavor wheel to identify gaps or off notes that require reformulation. Multiple iterations are often needed. Some spices may clump, certain acids might degrade in heat, and some flavor oils could lose their punch after just a few days in packaging. Stabilizers and carriers are used to protect volatile components, and microencapsulation techniques ensure that heat-sensitive ingredients only release during mastication, not while sitting in the bag. Once the flavor passes internal panels, the next phase is consumer testing. In select cities, Doritos organizes blind taste tests, sometimes with up to 500 participants per flavor. Reactions are scored not only on flavor, but on memorability, uniqueness, and potential repeat purchase behavior. Statistical modeling software crunches this data to identify the most promising formulas. When a flavor is approved, it must be scaled up to factory levels without losing its integrity. Seasoning blends are manufactured in industrial blenders, often in batches of hundreds of kilograms. The bulk seasoning is tested for particle size, uniformity, moisture absorption, and flow behavior. During this phase, the seasoning is often reformulated slightly for stability, color consistency, and performance under high-speed drum tumbling. Then come the pilot runs. A limited quantity of chips is produced on a full-scale Doritos line using the new flavor. This lets engineers monitor how the seasoning behaves under actual production conditions, how well it sticks to the chip, whether it builds up on machinery, how the oil in the powder affects packaging line sensors. If issues arise, tweaks are made not just to the formula, but to the machinery settings as well. Finally, once all checks are passed, the new flavor enters full production, often accompanied by bold marketing campaigns and timed releases. Global coordination ensures that ingredients meet regional compliance, and new flavors often debut in test markets before rolling out broadly. These launches are tracked in real time, and consumer response loops back into the development pipeline, influencing which flavors stay, evolve, or disappear. This highly coordinated, scientific, and iterative approach allows Doritos to launch daring new flavors while maintaining the consistency and production efficiency that a global brand demands. Each new taste starts with creativity, but ends in finely tuned, factory-scale execution. In a modern Oreo manufacturing facility, key dry ingredients are delivered in bulk, often by rail cars or food-grade trucks, and are pneumatically conveyed into large storage silos made of stainless steel or epoxy-lined carbon steel. These silos are sealed from air and moisture and are connected to the factory's central control system. The main dry ingredients include unbleached, enriched wheat flour, processed cocoa powder, granulated sugar, and minor dry components like baking soda and salt. Each of these materials is handled in its own silo or hopper, and automated augers or vibratory feeders dispense precise quantities into batch weighing hoppers. These hoppers sit on load cells, sensitive scales that can measure down to a fraction of a gram. This is essential because the correct ratio of flour to cocoa to sugar directly affects not only the flavor, but also how the dough behaves under pressure during molding. If the cocoa content is even slightly too high, for instance, the dough may become too brittle and crack during forming. If it's too low, the wafers may bake up too soft, losing the crisp snap that defines an Oreo. Once the dry materials are batched, they are conveyed into a pre-mixing chamber. At this stage, powdered ingredients are briefly tumbled together to ensure initial homogeneity before liquids are added. Then it's time for the liquid components to enter the system. These include vegetable shortening, often a blend of palm and canola oil, along with a sugar syrup or glucose solution, invert sugar, lecithin, and vanillin or other flavoring agents. The fats and liquids are stored in temperature-controlled tanks and are metered into the mixer through heated pipes. The temperature of the fats is critical. Too cold, and they won't disperse evenly. Too hot, and they could melt too aggressively, breaking down the emulsion and affecting dough integrity. All of these components are combined in large jacketed horizontal mixers or double sigma arm batch mixers. These mixers are chosen for their ability to handle heavy, cohesive doughs while still ensuring thorough dispersion. Inside the mixer, paddles or blades knead the dough continuously, folding and stretching it to develop a uniform texture. The mixer operates under a specific time and speed profile, starting slow to incorporate the dry and wet components, then increasing speed to blend, then finishing with a gentle knead to avoid overworking the dough. The goal here is a dough that's soft but not sticky, cohesive but not tough. Sensors inside the mixing chamber monitor temperature and torque, two key indicators of dough readiness. If the dough becomes too warm from friction, it can become greasy and difficult to form clean edges in the molding machines. If it's undermixed, the ingredients won't be uniformly distributed, and inconsistencies in cookie size, color, and bake profile will result later on. Once the dough reaches its target specifications, it's discharged from the mixer through a hydraulically controlled trapdoor at the base of the mixing tank. The dough falls into a dough transport system, typically a set of conveyors or troughs lined with non-stick materials like Teflon or food-grade UHMW polyethylene. At this stage, the dough may still be slightly warm, around 30 degrees Celsius to 35 degrees Celsius, and has a dense, matte appearance with a strong cocoa aroma. Before moving to the forming machines, the dough must undergo a resting period in certain operations. This allows the flour to fully hydrate and any residual gases or trapped air to escape. In high-speed production environments, however, this rest period may be minimized or skipped altogether if the formulation is optimized for immediate processing. This completes the initial phase: ingredient intake, formulation, mixing, and dough discharge. Each step up to this point is carefully controlled by recipe management software that ensures no human error can affect batch consistency. Recipe locks, scanner-based operator identification, and redundant scale verification ensure each batch of Oreo wafer dough is made precisely to the specifications required to perform flawlessly in the next stage of the journey: shaping and embossing. Now that the chocolate wafer dough has been prepared with absolute precision, measured, mixed, and conditioned, it moves into one of the most visually iconic and mechanically fascinating phases in the Oreo production line: forming and molding. This step takes the dense, cocoa-rich dough and transforms it into thousands of uniformly sized, detailed cookie wafers, each embossed with the distinctive Oreo pattern. This is not simply cutting shapes out of dough, it's a highly engineered, high-speed process where consistency in shape, thickness, and surface detail must be maintained across millions of units every day. The freshly prepared dough is conveyed to a hopper positioned above a sheeter. This sheeter is a wide, stainless steel roller assembly that flattens the dough into a uniform sheet of specific thickness. The dough moves between a set of rollers, typically 2 or more steel cylinders calibrated to exact tolerances that compress it to the target height. For Oreo wafers, the final sheet is quite thin, often around 3 to 4 millimeters, with a consistent density and moisture distribution. Getting this thickness right is critical. If the sheet is too thick, the cookie may not bake evenly or could become too brittle. Too thin, and the cookies may crack, burn, or crumble during sandwiching. Sensors measure the thickness of the sheet continuously using laser or ultrasonic gauges. If deviations are detected, servo-driven actuators automatically adjust roller spacing to maintain precision. The sheeter also includes edge trimmers, small, motorized blades that cut off uneven or frayed edges of the dough sheet to keep the line uniform. The trimmed edges are collected by a scrap recovery system and reintroduced into the mixing system, minimizing waste without compromising freshness or quality. Once the dough sheet is perfected, it enters the rotary molder. This machine is central to the Oreo brand's identity, as it forms the shape, size, and embossed design of each cookie wafer. The rotary molder consists of 2 primary components: a rotating die roller and a pressure roller. The die roller is a cylindrical drum engraved with multiple cavities, each one precisely carved with the Oreo design. These cavities aren't just cosmetic. Their depth and contour dictate the final relief of the cookie surface. As the dough sheet passes between the die roller and pressure roller, each cavity punches into the dough, compressing it into shape and imprinting the Oreo design. The pressure roller, covered in food-safe rubber or polymer, pushes the dough up into the die cavities, ensuring a clean, complete mold. As the die drum continues rotating, the shaped wafers are extracted by a combination of mechanical pushes and vacuum assist systems, which gently remove the cookies from the cavities without smudging the design. These freshly molded cookie wafers are then transferred onto a wide mesh conveyor belt in a continuous, uninterrupted line. Each wafer is spaced evenly to allow for proper airflow in the next phase: baking. Meanwhile, the excess dough surrounding the cutouts, known as webbing, is carefully separated and sent back through the scrap system. This recovery loop is highly efficient, capturing nearly 100% of the unused dough and returning it to the mixer via chilled transport belts. To ensure product consistency, reworked dough is blended at a fixed percentage into fresh dough, preventing any changes in texture, flavor, or moisture that might result from over-processing. As the line of uniform, molded Oreo wafers advances, they approach the baking tunnel, one of the most thermodynamically sophisticated parts of the facility. The tunnel oven is a massive structure, often exceeding 30 meters in length, segmented into multiple temperature-controlled zones. Each zone is precisely tuned to manage the gradual dehydration and expansion of the cookie, ensuring even baking from edge to center. The ovens use convection, conduction, and in some cases, radiant heat, depending on the equipment manufacturer and regional factory specifications. The cookie wafers bake as they travel slowly through the tunnel, typically for a duration of 4 to 6 minutes. Conveyor speed, airflow rate, and internal oven temperatures are continuously adjusted via programmable logic controllers that interface with sensors monitoring internal humidity, surface temperature, and even color of the baking cookies using infrared imaging systems. The target bake is one where the cookie becomes crisp and fully set while retaining a slight moisture gradient at its core, enough to ensure it sandwiches cleanly without shattering, and holds up in milk without becoming soggy too quickly. Another crucial parameter monitored at this stage is cookie spread and diameter. Because the molded wafers expand slightly as they bake, their final size must fall within a fraction of a millimeter to ensure they'll match perfectly with their paired half during sandwiching. Edge blowout, where cookies develop uneven bulges or bubbles, is prevented by careful control of initial dough temperature, mold compression depth, and oven humidity during the first baking phase. As the cookies exit the oven, they are immediately passed through a staged cooling system. This phase is designed to gently bring the cookies from their internal post-bake temperature of roughly 160 degrees Celsius down to ambient room temperature. Cooling too quickly can cause the wafers to crack, warp, or experience checking, tiny surface fractures that affect aesthetics and structural integrity. To avoid this, the conveyor slowly moves the wafers through a series of cooling zones with progressively decreasing airflow temperatures. High-volume fans push filtered, dehumidified air over the wafers in a cross-flow pattern that cools them evenly on all sides. By the time the wafers reach the end of the cooling tunnel, they are firm, crisp, and at a stable moisture level, typically around 1.5% to 2%. This ensures maximum shelf life, a satisfying crunch, and ideal compatibility with the creme filling in the next phase of production. They are now ready for alignment and pairing. Wafers are automatically aligned into dual streams using diverters and channeling guides. Conveyor belts, equipped with vision systems, scan for defects such as missing embossing, chips, discoloration, or breakage. These systems use high-speed cameras and AI-assisted pattern recognition to detect any imperfections in milliseconds. Rejected cookies are diverted to a waste collection hopper, and approved wafers continue forward to the sandwiching stage. With the Oreo chocolate wafer cookies fully formed, baked, and cooled, the production line now transitions into one of the most iconic and mechanically synchronized parts of the process: sandwiching. This stage involves the precise alignment of two delicate wafer halves around a carefully deposited swirl of creme filling, forming the complete Oreo cookie as we know it. What may seem like a simple task, placing filling between two cookies, is in fact a highly controlled and technically advanced process that prioritizes speed, accuracy, hygiene, and product consistency. The cooled wafers arrive at the sandwiching station via dual-lane conveyors that separate and feed cookies into two different orientations: bottom wafers and top wafers. The bottom wafers are destined to receive the cream filling, while the top wafers are held back momentarily, synchronized to arrive just as the filling has been deposited. Vision-guided pick-and-place arms or mechanical guides ensure that each cookie is properly positioned and oriented with the embossed design facing upward, especially important for branded recognition in the final presentation. The placement needs to be exact. Even a slight misalignment could result in uneven sandwiching or a crooked creme center, which would be rejected downstream. At the heart of the sandwiching line is the creme depositor. This component is engineered to dispense a precise amount of creme onto the center of each bottom wafer. The creme filling itself has been prepared earlier in the process and is stored in stainless steel holding tanks near the sandwiching line. The base creme is a blend of vegetable shortening, powdered sugar, and natural or artificial flavorings, aerated to achieve a smooth and creamy texture. It is kept at a controlled temperature, typically between 25 degrees Celsius and 30 degrees Celsius, to maintain flow consistency without being too runny or too firm. The creme is pumped into the depositor through a jacketed delivery line, which maintains temperature and prevents any hardening or separation. Inside the depositor, a rotary valve system or piston-driven nozzles release measured quantities of filling in circular swirls directly onto each passing wafer. The target deposition amount is extremely precise, usually around 3 grams per cookie for the original Oreo. For double stuff, the system is calibrated to deliver twice that volume, and the depositor nozzle height is adjusted accordingly to accommodate the larger swirl. The deposition speed is synchronized with the conveyor, meaning each swirl is deposited while the bottom wafer is in motion. To maintain consistent swirl shapes, the nozzle spins at a high RPM as it dispenses the cream. Sensors and imaging software track swirl size, height, and position. If the deposit strays from the central zone or falls outside weight tolerances, that cookie is automatically flagged and diverted. These sensors run continuously, sampling thousands of cookies per minute with extremely tight thresholds for variance. Once the creme is in place, the top wafer is gently placed onto the swirl. This is done by an overhead transfer arm or drop chute designed to lower each top cookie into place with just enough pressure to make contact without squashing the filling. The timing here is critical. Placing the top wafer too early could create smearing or incomplete adhesion, while placing it too late could allow the creme to set and result in a loosely held sandwich. Once the two halves make contact, a calibrated compression roller or paddle gently presses them together to create a uniform sandwich with a visible, even creme edge. The newly assembled Oreo cookies are then conveyed forward to undergo another round of quality inspection. At this stage, high-speed vision systems again scan for defects. These include cracked or broken wafers, misaligned sandwiches, off-center cream, or excess filling that has oozed out past the edges. Cookies that fail to meet standards are ejected via pneumatic pushers or retractable gates, landing in separate bins for non-conforming product. These rejected cookies are either discarded or recycled depending on factory policies and whether they passed earlier food safety checks. The good cookies move on to the next major phase, cooling and setting. Even though the creme filling is solid at room temperature, the act of depositing and sandwiching generates residual warmth, and the filling remains somewhat malleable for several minutes. To stabilize the sandwich structure and ensure long-term integrity during packaging and shipping, the cookies are passed through a controlled cooling tunnel. This tunnel gradually brings the product's temperature down to a stable point, typically just below ambient, which firms up the cream and locks in the sandwich's structural cohesion. As cookies exit the cooling tunnel, they are directed toward the packaging line. Here, the cookies are grouped and arranged into stacks or rows depending on the intended package format, whether it's a classic tray-style retail pack, a resealable pouch, a single-serving sleeve, or a multi-pack unit. For traditional packs, the cookies are guided into channels that group them into stacks, typically of 3 or more, which are then lowered into thermoformed plastic trays by robotic pick-and-place units. These trays help protect the cookies from damage and keep them organized for end-user convenience. Parallel to this, packaging film, pre-printed with branding, nutritional labels, and product information, is unwound from large rolls and fed into a form-fill seal machine. As the cookie-filled trays pass through the machine, the film is wrapped around the product, heat-sealed on all sides, and trimmed to size. Oxygen scavengers or desiccants may be inserted for freshness in some markets, depending on climate and shelf life requirements. For resealable packs, a Ziploc or peel-back adhesive strip is applied as part of the film sealing process, ensuring that consumers can open and close the package without reducing freshness. Each package unit is printed with a lot number, manufacturing date, facility code, and expiration date using high-speed thermal inkjet or laser printers. These codes enable full traceability and are cross-referenced with the production batch data stored in the factory's ERP system. From mixing and molding to creme filling and sealing, every step of the process can be traced back to specific machines, operators, shift schedules, and ingredient batches, an essential feature for food safety compliance and recall readiness. Once sealed, packages are conveyed to automated case packers. Here, robotic arms load the wrapped units into corrugated cardboard cartons, which are then glued or taped shut. These cartons are palletized according to preset patterns that optimize load stability and cube efficiency for shipping. Pallets are wrapped with stretch film, labeled with shipping barcodes and inventory data, and routed to the warehouse staging area. At this point, the Oreo cookies have completed their physical transformation from separate cocoa wafers and creme filling into a polished, fully packaged, ready-to-ship product. But before they leave the factory, they undergo a final quality audit. Samples from each batch are pulled from the finished goods line and tested by in-house sensory panels and laboratory staff. Taste, texture, aroma, appearance, and moisture content are evaluated to ensure that the product not only looks perfect, but delivers the consistent flavor and mouthfeel that Oreo is known for. Moisture levels are especially critical. Too high, and the cookie can lose its crispness during storage. Too low, and it can become brittle or stale. Texture analyzers apply mechanical pressure to the cookies to evaluate crunch resistance and breaking force, while gas chromatography is used to verify flavor compound profiles. Packaging integrity tests include drop tests, seal strength verification, and temperature cycling simulations that mimic transport and storage conditions across various markets. Once these final inspections are passed, the cookies are released for distribution. Pallets are loaded into climate-controlled trucks or containers, routed through regional distribution centers, and ultimately arrive at retail outlets, vending networks, or direct-to-consumer channels. With the Oreo cookie now fully assembled, inspected, packaged, and palletized, the final phase of the in-factory process is dedicated to the logistics, storage, inventory control, and outbound quality assurance systems that prepare the product for global distribution. While it may seem like the technical complexity is behind us, this stage involves its own set of sophisticated workflows designed to ensure that every package remains pristine, traceable, and shelf-stable for months after production, regardless of whether it ends up in a small, rural convenience store or a high-volume urban supermarket. The finished pallets of Oreos are moved from the end-of-line palletizing systems into a dedicated finished goods warehouse. This space is part of the factory complex, but isolated from production to prevent cross-contamination and maintain temperature and humidity stability. Oreo cookies, especially those with creme fillings, are highly sensitive to environmental changes. Excessive heat can soften the filling or compromise the packaging seal, while high humidity can cause moisture migration into the wafer, leading to loss of crispness. To combat these risks, the warehouse is maintained at a tightly regulated temperature, typically between 18 degrees Celsius and 22 degrees Celsius, with relative humidity kept under 50%. The facility is segmented into climate zones for different packaging formats, with certain areas reserved for international shipments that may require added humidity resistance or longer storage durations. Air handlers, industrial-grade dehumidifiers, and air filtration systems constantly regulate and cycle the air to maintain these parameters. Even the lighting systems are designed to minimize UV exposure, which could, over time, degrade packaging ink or food contact films. Once inside the warehouse, each pallet is scanned and logged into a warehouse management system. This system is fully integrated with the factory's enterprise resource planning software and allows operators to track not only where each pallet is stored, but exactly what production line, time, and ingredient lot was used to produce its contents. Each pallet label includes a unique serial number, barcode, and QR code that links to this full production history. This traceability is essential not just for internal logistics, but also for compliance with food safety regulations around the world, which require manufacturers to be able to track every product from raw ingredient to final point of sale. The WMS automatically arranges pallets by product type, batch date, and destination. Those scheduled for export may be routed to a separate staging zone where they will be checked for compliance with international packaging laws. Different markets may require translated labels, adjusted nutritional formats, or modified lot codes. Some export destinations also require additional tests, such as microbial swabs or accelerated shelf life sampling, to meet foreign government regulations. These are performed in an adjacent quality control annex, and only upon clearance are these pallets released to outbound logistics. Before any Oreo shipment leaves the facility, it undergoes a final visual inspection for physical damage to packaging, tamper seals, and box integrity. Any visible damage may indicate mishandling during internal transit or weak spots in pallet stability. Operators are trained to look for warped trays, compromised seals, or even small tears in the flow wrap film that could affect product freshness. Should any defect be discovered, that pallet is held for secondary inspection, and depending on severity, it may be repackaged or scrapped entirely. At this point, logistics coordinators use automated routing systems to schedule outbound shipments. These systems factor in geographic location, delivery deadlines, climate conditions, and truck availability. For example, shipments bound for warmer climates during the summer may be prioritized for insulated or refrigerated trucks to prevent the creme from softening. Long-haul shipments may be routed through distribution centers that offer cross-docking or climate-controlled storage to preserve product quality along the supply chain. The loading dock itself is operated with precision. Trucks arriving at the facility must be cleaned, inspected, and approved before any Oreo products are loaded. This includes visual inspection for pests, residue from prior shipments, and confirmation that the trailer temperature is within specification. Only after a truck passes these inspections does the facility open the dock door and begin the loading sequence. Robotic forklifts or human operators load the pallets according to pre-planned diagrams that ensure weight is evenly distributed and product is easily accessible at the destination. Each shipment is logged with time, driver ID, carrier information, route ID, and estimated delivery window. Once loaded, trucks are sealed with tamper-evident locks and dispatched with digital shipping documents, including delivery confirmations and scanned QR codes for receiving teams. The WMS updates the ERP system in real time, closing the inventory loop and marking the batch as shipped. This inventory and logistics traceability is crucial for meeting compliance with global food safety standards like the Global Food Safety Initiative, hazard analysis, and critical control points, and ISO 22000. Even after the Oreo product leaves the plant, the factory remains connected to its life cycle through digital feedback systems. Retailers and distributors have access to portal-based interfaces where they can report damages, delayed deliveries, or unexpected inventory issues. Returned products are scanned upon arrival at reverse logistics zones where factory staff investigate issues, analyze production records, and determine root causes. In cases where errors are found, such as premature staleness, flavor imbalance, or packaging failure, continuous improvement protocols are triggered to address the upstream causes. While these systems function to protect the product, they also feed into a broader factory goal: performance analytics, and continuous optimization. The data from every shipment, temperature logs, shipping duration, breakage rates, seal integrity, and even consumer complaints is compiled into dashboards reviewed weekly by production leads, QA managers, and logistics coordinators. These dashboards enable the factory team to track KPIs like OTIF, defect per million rates, inventory turnover, spoilage reduction, and carbon footprint per pallet. Some Oreo plants are moving even further towards sustainability at this stage of production. Cardboard shipping boxes are made with recycled content and are themselves fully recyclable. Pallet wrap films are being downgauged or replaced with biodegradable alternatives. Facilities are experimenting with hybrid electric fleet partnerships or rail transport instead of trucks to reduce emissions. In select markets, even the plastic trays inside Oreo packs have been redesigned for recyclability, and clear labels now inform consumers on proper disposal. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean to fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers, often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun's structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated. Five Guys moves thousands of pounds of beef and buns through a supply chain so intense it runs like a high-speed burger machine. Behind every fresh, made-to-order meal is a massive factory system designed to deliver consistent flavor with zero shortcuts. In this documentary, we go inside the operation powering one of America's most iconic burger chains, from raw ingredients to grill-ready perfection. Unlike many fast food chains that rely heavily on pre-cooked, frozen, or highly processed food products, Five Guys has built its entire business model on quality, freshness, and simplicity. That simplicity, however, hides a remarkably complex and carefully controlled supply chain that delivers consistent, high-quality ingredients to thousands of restaurants across the US and internationally. The journey of a Five Guys burger begins not in the kitchen, but at the factory, processing plant, and farm. The most critical component of any Five Guys burger is the beef. The company is famously particular about the type of beef it uses, never frozen, 100% fresh, and containing no fillers or additives. All Five Guys burgers are made from ground chuck, an 80/20 lean-to-fat ratio that balances flavor and moisture retention. The sourcing process begins at the cattle farm. Five Guys works with a network of beef suppliers located throughout the US and Canada, primarily sourcing from ranches that meet rigorous standards for breed, feed, and animal handling. These standards require that cattle are fed a grain-based diet with a strong emphasis on quality and marbling rather than lean meat content. Cattle are raised under conditions that follow USDA guidelines, and many of Five Guys suppliers participate in third-party animal welfare audits. The cattle are processed in USDA-inspected facilities that are required to meet strict sanitation, temperature, and traceability requirements. Upon slaughter, carcasses are dry-aged in chilled holding rooms to develop flavor and improve tenderness, typically for a minimum of 24 to 48 hours, depending on the processor. The next phase happens at industrial meat processing plants, where the chuck sections are broken down and inspected. These plants are not typical slaughterhouses. They're highly automated production environments that specialize in precision meat portioning and grinding. Only specific muscle groups from the chuck are used in Five Guys' blend, and these cuts are separated, trimmed, and visually inspected for sinew, silver skin, and excessive fat content. Once portioned, the chuck is passed through industrial meat grinders equipped with die plates that produce uniform, medium-coarse ground beef. The grinders are chilled to maintain the meat's structural integrity, typically operating in ambient temperatures of 34 degrees Fahrenheit to 39 degrees Fahrenheit. During grinding, the meat's temperature is constantly monitored using inline thermocouples. If the internal temperature of the grind rises above 40 degrees Fahrenheit, the system automatically shuts down to avoid potential bacterial growth. Importantly, no seasonings, preservatives, or binders are added. This is pure beef, ground and immediately formed into patties using hydraulic patty forming machines. These machines compress the ground beef into uniform discs using precision molds that form 3.3 ounce patties, the size used to build each layer of a Five Guys burger. The patties are shaped gently, not compressed too tightly, to retain tenderness and prevent a dense, chewy texture. Immediately after forming, the patties are layered with food-safe paper interleaves and placed into rigid plastic trays, each separated to prevent sticking or pressure damage. These trays are stacked, shrink-wrapped, and labeled with batch numbers, timestamps, and facility codes. Each batch is also linked to its source lot for full traceability. If an issue ever arises, Five Guys can track the beef back to the exact processing date, plant line, and originating herd. Now, perhaps most famously, Five Guys insists on a never-frozen supply chain. This policy presents a significant challenge at scale. Unlike chains that freeze patties for storage and ship them globally, Five Guys must operate a highly synchronized cold logistics system. Once patties are packed, they're loaded into refrigerated trucks operating at 34 degrees Fahrenheit to 36 degrees Fahrenheit. These trucks are equipped with GPS and temperature tracking to ensure compliance with cold chain protocols throughout the journey. The patties are transported to regional distribution centers often no more than a day's drive from the restaurants they supply. These facilities are designed to receive, inspect, and hold the beef for only a short window, usually no more than 7 days. If any shipment arrives even a few degrees above temperature or outside of its acceptable delivery window, it is rejected outright. From the distribution hub, the beef is delivered directly to Five Guys restaurants in cold-packed containers, where it is stored in the restaurant's walk-in cooler and used within 48 hours. While beef is one pillar of the operation, another critical component handled at the industrial level is the potato. Five Guys fries are almost as iconic as their burgers, and the company is equally obsessive about how they're sourced and handled. The only potato variety used in their fries is the Idaho Russet Burbank, known for its high starch content and firm texture, which allows it to hold up through the unique double frying process that Five Guys uses in store. At the agricultural level, potatoes are contracted from farms in the Pacific Northwest, with many coming from family-owned operations in Idaho and Washington. Potatoes are harvested in the fall and stored in climate-controlled warehouses known as potato cellars, where temperature, humidity, and ventilation are tightly regulated to preserve them for year-round use. These facilities use continuous air circulation and CO2 scrubbing systems to prevent spoilage and sprouting. The raw, unpeeled potatoes are trucked to centralized packing plants where they are washed, sorted by size, and loaded into breathable mesh sacks. Unlike frozen fries, which are peeled, blanched, and par-fried in industrial plants, Five Guys potatoes remain entirely raw. There is no industrial cutting, freezing, or seasoning. This makes the logistics much more complex, as raw potatoes are sensitive to bruising, sprouting, and microbial spoilage if handled improperly. After sorting and packing, the potatoes are placed on ventilated pallets and shipped in temperature-controlled trucks to distribution centers and directly to restaurants. Each delivery includes information on farm origin, harvest date, and even the potato storage conditions. When they arrive at the restaurant, they're stored in a dry, cool area, often stacked openly near the front of the store, which has become a visual hallmark of Five Guys locations. To recap, the beef is ground fresh, formed, and shipped cold, not frozen, with strict temperature and traceability controls. The potatoes are delivered raw, whole, and unprocessed, ensuring that every step from frying to seasoning happens in-store by hand. These two ingredients alone demand an industrial choreography that's unlike most fast food chains. And this is just the beginning. With the beef patties and fresh-cut fries prepared and shipped under cold chain precision, the next essential ingredient in the Five Guys burger system comes into focus: the bun. Unlike the patties and potatoes, which are either ground or cut at industrial scale, the buns are crafted in high-output bakeries designed to balance handcrafted quality with the consistency needed to serve thousands of locations daily. This stage of production, though it may seem simple on the surface, involves rigorous formulation, batch precision, fermentation control, and timed logistics to ensure that every burger bun meets the brand's exacting standards. Five Guys uses a proprietary bun recipe, one that's softer and slightly sweeter than standard hamburger buns. This isn't a generic bakery item. It has been formulated specifically to absorb the juices of fresh patties while remaining sturdy enough not to disintegrate during handling. The dough is made daily in regional bakeries contracted exclusively by Five Guys, meaning that each region has its own centralized baking partner to keep delivery times short and the product ultra fresh. The bun dough starts with a mix of enriched wheat flour, water, yeast, sugar, whole eggs, salt, and soybean oil. A small amount of dough conditioner, such as ascorbic acid or enzymes, may be included to regulate gluten strength and improve shelf stability for the short duration these buns spend in transit. Every ingredient is loaded into massive spiral or planetary mixers capable of handling several hundred kilograms of dough per batch. These mixers operate under batch control systems that log ingredient weights via integrated floor scales. Dough temperature is regulated using chilled water injection and jacketed mixing bowls to keep yeast fermentation in check, especially during high output shifts. Once mixed, the dough is allowed to rest for a brief pre-fermentation phase, often referred to as bench rest. This allows the gluten network to begin developing while gas bubbles from yeast fermentation begin forming. From there, the dough is conveyed to a divider rounder system, an automated machine that portions dough balls and gently shapes them into smooth rounds using mechanical cups or centrifugal motion. The precise size is critical, as Five Guys buns must fit the patty exactly, with no overhang or shrinking during grilling. The standard target weight for each bun is usually between 78 and 82 grams, with tolerances of less than +1 g. Once portioned, the dough balls are loaded onto proofing trays and transferred into a temperature and humidity-controlled proofing chamber. This chamber mimics the conditions of a traditional proofer, around 90 degrees Fahrenheit and 85% humidity. Inside, the yeast activity causes the dough balls to rise and expand, forming the signature airy texture of Five Guys buns. This proofing stage usually lasts 45 to 60 minutes, depending on ambient conditions and bakery altitude, with real-time CO2 monitoring systems in place to fine-tune time adjustments. After proofing, the buns are topped with sesame seeds using mechanical seeders positioned just above the conveyor. The trays then enter the baking oven, a long, continuous belt oven heated by convection and radiant sources, set typically between 375 degrees Fahrenheit and 425 degrees Fahrenheit. Each bun passes through the oven on a belt that moves at a consistent speed, completing the bake in about 12 to 15 minutes. Internal product probes are used to confirm that each bun reaches a core temperature above 190 degrees Fahrenheit, ensuring full gelatinization of starches and proper set of the protein matrix. Once baked, the buns move through a rapid cooling tunnel to bring their internal temperature down to below 90 degrees Fahrenheit as quickly as possible. This prevents moisture condensation within packaging and stabilizes the product for transport. Cooling too slowly could encourage mold growth or collapse the bun structure. The cooled buns are then passed to an automated slicer that splits each bun horizontally, preparing it for use in restaurants. The slicing is done with oscillating serrated blades that operate in sync with the belt speed to avoid tearing or compression. The sliced buns are carefully packed into breathable plastic sleeves, typically holding 6 to 8 buns per pack, and then into cardboard cartons. These cartons are labeled with batch numbers, bakery codes, timestamps, and use-by dates. The target shelf life is short, usually no more than 5 days, including shipping and storage time in line with Five Guys' no freezer policy. Because the buns contain no artificial preservatives, they require tight turnaround from production to consumption. Logistically, the buns are shipped daily from bakeries to distribution centers and then to restaurants. Many bakeries operate overnight shifts to ensure that fresh buns can be delivered in the early morning hours for that day's service. Trucks used for transport are not refrigerated, but the buns are loaded in temperature-controlled staging areas and packed in sealed corrugated boxes to maintain freshness during transit. Any deviation in delivery, timing, or packaging temperature triggers a rejection at the restaurant level. In store, the buns are stored at room temperature in designated bread racks, often rotated using FIFO principles. Staff members are trained to inspect buns visually and by touch. Any signs of excess firmness, moisture, or spotting lead to immediate disposal. Each bun is hand-prepared on-site, toasted on a grill with a light coating of melted butter before it becomes the vehicle for the burger build. This final touch, though simple, is only possible because of the structural integrity and texture delivered by the bakery's industrial process. Now that the core components of a Five Guys burger are accounted for, the beef, the fries, and the buns, it's time to examine the supporting elements that complete the burger experience: bacon, cheese, toppings, and condiments. These items may seem simple, but each is chosen and prepared with deliberate intent and, in most cases, centralized at an industrial level before being delivered to restaurants. Starting with bacon, Five Guys sources thick-cut, naturally smoked strips from approved pork processors in the US. The bacon is not fully cooked at the factory. Instead, it's partially cooked or pre-rendered to about 60 to 70% doneness, then chilled and vacuum packed in clear plastic pouches. These pouches are labeled and sorted by weight and count per case, with each case tagged for traceability. The bacon is cooked to completion in the restaurant, where staff lay it flat on the grill and crisp it to order. This two-step process, initial industrial cooking followed by final preparation, ensures food safety, flavor development, and grease reduction. The journey begins with sourcing green coffee beans. Factories procure these beans in large quantities from coffee-growing regions such as Brazil, Colombia, Vietnam, and Ethiopia. Since instant coffee requires consistent flavor profiles, manufacturers often blend beans from various regions to create a balanced and standardized flavor. Upon arrival at the factory, the green coffee beans are subjected to rigorous quality control checks. Samples are tested for size, moisture content, and defects to ensure the beans meet the factory's standards for processing. Once approved, the beans are stored in massive silos made of food-grade stainless steel or aluminum to protect them from contamination, pests, and humidity. These silos are equipped with automated systems that precisely dispense beans onto the production line. The first major step in processing the beans is cleaning. Coffee beans, even after being cleaned at their origin, may still contain impurities such as dirt, stones, sticks, or metal fragments. In the factory, the cleaning process involves several stages. Vibrating screens sift the beans to remove large debris, while air classifiers blow away lighter materials like husks or dust. Magnets are used to extract any metallic particles. Some factories also employ optical sorting machines, which use cameras and sensors to identify and remove defective beans or foreign objects. This thorough cleaning ensures that only high-quality beans proceed to the roasting stage. Roasting is a critical step in developing the rich, complex flavors of coffee. Factories use industrial coffee roasters, which can process thousands of pounds of beans per hour. The roasting process is controlled by highly advanced systems that allow operators to customize the roast profile for specific flavor outcomes. For instant coffee, medium to dark roasts are commonly used, as they bring out bold flavors that translate well into the final soluble product. Roasting temperatures typically range between 370 and 540 degrees Fahrenheit, depending on the desired flavor profile. During roasting, the beans undergo the Maillard reaction, a chemical process that creates the characteristic aromas and flavors of coffee. The roasting equipment includes temperature sensors and real-time monitoring systems to ensure uniform roasting across large batches. Once the roasting is complete, the beans are cooled rapidly to stop the roasting process and prevent overcooking. Factories use air cooling systems or water spray cooling, depending on the setup. Cooling is an important step, as improperly cooled beans can lose their flavor or become brittle. After cooling, the beans are sent to grinding machines. The grinding stage reduces the roasted coffee beans into smaller particles, which will be used for the brewing process. Factories use industrial grinders, such as roller mills or hammer mills, capable of producing a consistent grind size. The grind size is crucial because it affects the extraction process that follows. For instant coffee, a relatively coarse grind is typically used to optimize the brewing process in the factory. The ground coffee is then stored in intermediate holding bins, where it is kept fresh until it is ready to be brewed. Brewing is the next major step in instant coffee production, and it is carried out on an industrial scale. Massive brewing systems, similar to oversized percolators, are used to extract the soluble compounds from the ground coffee. These systems consist of large stainless steel extraction tanks or columns, which are designed to hold thousands of gallons of water and coffee grounds. Hot water is circulated through the coffee grounds at precise temperatures and pressures, mimicking the brewing process used at home, but on a much larger scale. Typically, water temperatures range between 190 and 205 degrees Fahrenheit, and the brewing time is carefully controlled to maximize flavor extraction while minimizing bitterness. The brewed coffee concentrate, a liquid containing the extracted soluble compounds, is then filtered to remove the spent coffee grounds. Factories use advanced filtration systems, such as centrifugal separators or fine mesh filters, to ensure that no solid particles remain in the liquid. The spent grounds are often dried and repurposed as fertilizer or biomass fuel, making use of every part of the raw material. At this stage, the coffee concentrate is a highly aromatic liquid, but it is still far from the final product. The challenge is to transform this liquid concentrate into a stable, dry, and soluble form. Factories use one of two main methods for this: spray drying or freeze drying. Spray drying is a fast and cost-effective method that is commonly used to produce instant coffee powder. The coffee concentrate is first preheated to reduce its moisture content. It is then pumped into a tall, spray drying chamber equipped with nozzles that disperse the liquid into fine droplets. At the same time, hot air, typically around 480 degrees Fahrenheit, is blown into the chamber. As the droplets fall through the chamber, the water in the coffee concentrate rapidly evaporates, leaving behind fine coffee powder. Spray drying is efficient and capable of processing large volumes, but the high temperatures can sometimes lead to a slight loss of flavor and aroma. Freeze drying, on the other hand, is a more delicate and sophisticated process that better preserves the natural flavors and aromas of coffee. The coffee concentrate is first frozen at extremely low temperatures, usually around 40 degrees Fahrenheit, to form solid slabs or granules. These frozen coffee pieces are then placed in a vacuum chamber. Inside the chamber, the frozen water in the coffee undergoes sublimation, a process where ice turns directly into vapor without passing through the liquid phase. This method requires precise control of temperature and pressure and takes longer than spray drying, but it produces high-quality granules of instant coffee that dissolve easily in water. After the drying process, the instant coffee is sifted and graded by particle size to ensure uniformity. Any oversized or undersized particles are removed, and the coffee is blended to create a consistent final product. Factories conduct rigorous quality control tests at this stage, including flavor analysis, solubility testing, and moisture content measurement. These tests ensure that the instant coffee meets the desired standards for flavor, aroma, and texture. Packaging is the final step in the production process, and it is designed to protect the coffee from moisture and preserve its freshness. The dried instant coffee is transported to high-speed filling machines, which dispense precise amounts of coffee into jars, tins, or pouches. Factories use nitrogen flushing systems to replace oxygen in the packaging, as oxygen can degrade the coffee over time. The jars are sealed with airtight lids, while pouches are heat sealed to maintain freshness. After sealing, the packages move to labeling stations, where automated systems apply branding, ingredient lists, and expiration dates. Each package undergoes a final inspection using vision systems to ensure there are no defects in the seals or labels. Once approved, the packages are packed into cartons or cases using robotic packing systems and prepared for shipping. Pallets of instant coffee are stacked and wrapped for stability before being loaded onto trucks or containers for global distribution. Throughout the entire process, factories rely on advanced automation and engineering to ensure efficiency and consistency. Programmable logic controllers and supervisory control and data acquisition systems monitor and control every stage of production, from roasting and brewing to drying and packaging. Real-time data on temperature, pressure, humidity, and other parameters allows operators to make precise adjustments as needed, minimizing waste and ensuring high-quality output. Hygiene and food safety are also paramount in instant coffee production. Production areas are designed with food-grade stainless steel surfaces, seamless flooring, and clean room environments to prevent contamination. Positive air pressure systems are used to keep airborne particles out of critical areas, and employees are required to follow strict hygiene protocols, including wearing protective clothing and adhering to cleaning schedules. Factories are regularly inspected and certified to meet international food safety standards. Inside a tea factory, the transformation of fresh tea leaves into the familiar tea bags, loose leaf tea, or powdered varieties is a carefully orchestrated process. It is a seamless blend of tradition, precision engineering, and science. Every step of the way, from leaf intake to packaging, is designed to preserve the flavor, aroma, and quality that tea enthusiasts have come to expect. While the type of tea being produced, whether black, green, oolong, or white, dictates specific steps in the process, the overall journey is one of meticulous attention to detail, where both manual expertise and advanced machinery play vital roles. The process begins at the tea gardens, where leaves from the Camellia sinensis plant are plucked at peak quality. For most teas, workers handpick only the top 2 leaves and a bud from each branch, as these tender parts of the plant produce the best flavor and aroma. After harvesting, the leaves are transported to the factory as quickly as possible to prevent spoilage or fermentation during transit. Many tea factories are strategically located near plantations to minimize delays and ensure freshness. Upon arrival at the factory, the tea leaves are weighed and inspected for quality. Modern tea factories are equipped with automated intake systems that separate leaves from debris such as twigs or foreign matter. Vibrating conveyor belts or mechanical sieves are commonly used at this stage to remove unwanted materials. For higher grade teas, additional manual inspections may be carried out to ensure only the finest leaves proceed to the next step. The fresh leaves are then carefully spread out in thin layers on large trays or conveyor belts, marking the beginning of the first stage in tea processing. Withering. Withering is a critical step in tea production, as it reduces the moisture content of the fresh tea leaves and prepares them for the subsequent stages of processing. In the factory, withering is typically carried out in withering troughs, long, shallow trays equipped with a system of fans and controlled airflow. Fresh tea leaves are laid out on these trays, and air is circulated over them for several hours to slowly remove moisture. For black tea, withering may last anywhere from 12 to 18 hours, while green tea requires a shorter withering time, as it needs to retain more of its fresh, grassy flavor. Temperature and humidity are carefully controlled using automated climate systems to ensure consistent results. During this stage, the leaves become softer and more pliable, making them ready for rolling. The next stage is rolling, where the tea leaves are twisted and shaped to release their essential oils and initiate oxidation if required, as with black and oolong teas. Factories use large mechanical rolling machines equipped with heavy, grooved plates or rollers. These machines apply pressure to the leaves, breaking down their cell walls and releasing their natural juices. The released juices react with oxygen in the air, beginning the oxidation process that gives black tea its characteristic flavor and color. Rolling machines can be adjusted to produce different shapes and textures, depending on the type of tea being made. For example, green teas may be rolled into tight pellets for varieties like gunpowder tea, while black teas are often left in long, wiry shapes. At this point, the production process diverges depending on the type of tea being manufactured. For black tea, oxidation is the next key step. Oxidation, often mistakenly referred to as fermentation, is a chemical process that darkens the tea leaves and develops the rich, robust flavors associated with black tea. In factories, oxidation typically takes place in large, temperature-controlled rooms, where rolled tea leaves are spread out on trays or conveyor belts. These rooms maintain a controlled environment with high humidity and a temperature of around 77 to 86 degrees Fahrenheit. The leaves are periodically monitored to ensure they achieve the desired level of oxidation, which can take anywhere from 30 minutes to several hours, depending on the tea. As the leaves oxidize, they turn from green to a reddish-brown color, releasing the aromatic compounds that define black tea. In contrast, for green tea production, oxidation is intentionally prevented. To preserve the vibrant green color and fresh vegetal flavor of the leaves, factories employ a process called fixation, also known as kill green. This step involves heating the leaves immediately after rolling to deactivate the enzymes that cause oxidation. Factories use either steam or dry heat for this purpose. For Japanese-style green teas, like sencha, the leaves are steamed in specialized machines, while Chinese-style green teas are often pan-fried in large heated woks or rotating drum roasters. Fixation requires precise temperature control, as overheating can burn the leaves and underheating can fail to stop oxidation completely. Once oxidation or fixation is complete, the next step is drying, which reduces the moisture content of the tea to make it shelf stable. Drying is typically carried out in large industrial dryers or ovens equipped with temperature controls and airflow systems. Conveyor belt dryers, in which the leaves are gradually moved through a heated chamber, are common in large-scale tea factories. The temperature during drying ranges from 194 to 248 degrees Fahrenheit, depending on the type of tea and the desired final moisture content, which is usually around 3 to 5%. This step is crucial for locking in the flavor and aroma of the tea while ensuring it will not spoil during storage. After drying, the tea leaves are sorted and graded. In the sorting process, leaves are separated by size, shape, and quality using a combination of vibrating sieves, air separators, and optical sorting machines. Whole leaves, broken leaves, and small particles are separated into different grades, which are used for various tea products. For instance, whole leaves are often reserved for premium loose-leaf teas, while smaller particles are used for tea bags. Some factories also employ advanced laser sorting machines that can detect and remove any remaining foreign objects or off-spec leaves. Blending is another key step in tea production, especially for brands that aim to create consistent flavor profiles. Many teas are blended by mixing leaves from different regions, harvests, or even types of tea. Blending is carried out in large rotating drums or mixing machines, where precise quantities of different teas are combined to achieve the desired flavor. For flavored teas, additional ingredients such as dried fruit pieces, herbs, or essential oils are added during this stage. For example, Earl Grey tea is made by blending black tea leaves with bergamot oil, while chai blends often include spices like cinnamon, cardamom, and cloves. Once the tea has been blended and sorted, it is ready for packaging. Packaging is a highly automated process in modern tea factories. For loose-leaf tea, the leaves are weighed and sealed in airtight bags, tins, or foil-lined pouches to preserve freshness. For tea bags, the leaves are measured and packed into filter paper, which is then cut and sealed into individual tea bags using high-speed machines. Many factories also produce pyramid-shaped tea bags, which allow for larger leaves and better infusion. After filling, the tea bags are placed into cartons or boxes, which are sealed and labeled with branding, lot numbers, and expiration dates. Throughout the entire process, quality control plays a vital role in ensuring the tea meets rigorous standards. Factories employ trained tea tasters who sample the tea at various stages of production to assess its flavor, aroma, and appearance. Advanced laboratory equipment is also used to measure moisture content, microbial activity, and other parameters that affect the quality and safety of the final product. Additionally, factories must comply with food safety regulations and certifications, such as ISO 22000 or HACCP, to ensure their tea is safe for consumption. Cocoa powder, the cornerstone of countless recipes from rich chocolate cakes to creamy hot cocoa, is the product of a complex and fascinating manufacturing process that combines agricultural expertise with advanced industrial engineering. Behind every tin or packet of cocoa powder lies a detailed, multi-step operation where raw cacao beans are transformed into the fine, flavorful powder that has become a staple ingredient in kitchens around the world. This process begins on cacao farms and culminates in a factory where specialized equipment and precise techniques ensure the consistency, flavor, and quality of the finished product. Let's take an in-depth journey into how cocoa powder is made, exploring each stage of the process, from bean to powder. The story of cocoa powder begins with the cacao tree, which thrives in tropical regions near the equator, such as West Africa, Southeast Asia, and Central and South America. The cacao tree produces pods that contain cacao beans surrounded by a sweet, sticky pulp. These beans are the raw material for cocoa powder. Once harvested, the pods are split open to extract the beans, which are then immediately subjected to the first critical step in the process: fermentation. Fermentation is a natural and essential process that develops the flavor precursors in cacao beans. After being removed from the pods, the beans and their surrounding pulp are placed into shallow wooden boxes or large banana leaf-lined baskets, where they ferment over a period of 5 to 7 days. During this time, natural yeasts and bacteria break down the sugars in the pulp, generating heat and causing the temperature in the fermentation pile to rise significantly, often reaching over 120 degrees Fahrenheit. This heat triggers a series of chemical reactions within the beans, developing their characteristic chocolate flavor while reducing bitterness. The beans are turned periodically to ensure even fermentation and prevent spoilage. Once fermentation is complete, the beans are removed from the boxes or baskets and sent to the next stage: drying. Drying is critical for stabilizing the fermented beans and reducing their moisture content to a level suitable for storage and transport. Traditionally, cacao beans are dried under the sun, spread out in thin layers on large drying racks or patios, and turned regularly with wooden rakes to ensure even drying. In modern cocoa production, factories may use mechanical dryers when weather conditions are unsuitable for sun drying or to speed up the process. These machines blow heated air over the beans to achieve the target moisture content, which is usually around 6 to 7%. Proper drying is essential because any excess moisture could lead to mold growth during storage or shipping. Once dried, the beans are sorted, graded, and packed into jute bags or bulk containers, ready for shipment to processing facilities. Upon arriving at the cocoa processing factory, the dried cacao beans are carefully inspected for quality. Factories use advanced optical sorting machines equipped with cameras and lasers to identify and remove defective beans, such as those that are cracked, moldy, or undersized. Any remaining debris, like stones or twigs, is removed using vibrating screens and air separators. Once the beans are cleaned, they are stored in large silos made of food-grade stainless steel which protects them from contamination while allowing for easy access as the beans move through the production line. The first step inside the factory is roasting, a critical stage that brings out the rich chocolatey aroma and flavor of the beans. Industrial roasters are designed to handle large volumes of cacao beans, roasting them at precise temperatures that can range from 250 to 300 degrees Fahrenheit. The exact temperature and duration of roasting depend on the type of cocoa powder being produced, as darker roasts develop more intense flavors, while lighter roasts preserve subtle fruity or floral notes. During roasting, the shells of the beans become brittle, and the internal nibs, which contain the cocoa solids and cocoa butter, begin to separate from the shell. Sensors and computer-controlled systems monitor the roasting process to ensure consistency across batches. Once roasting is complete, the beans are rapidly cooled, using air or water to prevent overcooking. The next stage is winnowing, where the roasted beans are cracked open to separate the nibs from the outer shells. This process is carried out using winnowing machines, which use a combination of mechanical rollers and air currents to break the shells and blow them away. The result is a pile of clean, roasted nibs, which are the purest form of cacao and the raw material for all cocoa products. The nibs are then ground into a thick, viscous liquid known as cocoa liquor, despite containing no alcohol. The grinding process involves heavy-duty industrial grinders, such as roller mills or stone grinders, which crush the nibs into tiny particles. This process releases the natural cocoa butter within the nibs, creating a smooth liquid that flows easily. The particle size is reduced to less than 30 microns during this stage to ensure a silky texture. Cocoa liquor is the base ingredient for many chocolate products, but for cocoa powder production, the focus shifts to separating the two main components of the liquor, cocoa solids and cocoa butter. The separation of cocoa solids and cocoa butter is achieved through pressing. Cocoa liquor is fed into hydraulic or screw presses, which apply immense pressure, up to 6,000 pounds per square inch, to squeeze out the cocoa butter. This process leaves behind a solid cake of compressed cocoa solids. The extracted cocoa butter is collected and filtered for use in other products, such as chocolate bars, cosmetics, or pharmaceuticals. Meanwhile, the cocoa cake, which still contains a small amount of residual fat, becomes the foundation for cocoa powder. The cocoa cake is cooled and broken into smaller chunks before being fed into pulverizing machines, where it is ground into a fine powder. Factories use various types of grinding equipment, such as pin mills or ball mills, to achieve the desired particle size for cocoa powder. This step is critical for ensuring that the final product has a consistent texture and dissolves easily in liquids. The fineness of cocoa powder can vary depending on its intended use. For example, baking-grade cocoa powder is typically ground finer than drinking cocoa. At this point, the cocoa powder is almost ready, but one additional process may take place depending on the type of cocoa being produced: alkalization, also known as Dutch processing. Alkalization involves treating the cocoa powder with an alkaline solution, such as potassium carbonate. This process neutralizes the natural acidity of the cocoa, darkens its color, and gives it a smoother, milder flavor. Alkalized cocoa powder is often used in baking and beverages, as its reduced acidity reacts differently with leavening agents like baking soda. Once the cocoa powder is fully processed, it undergoes rigorous quality control tests to ensure it meets the manufacturer's standards. Samples are tested for flavor, color, pH levels, fat content, and particle size. Factories use advanced laboratory equipment, such as spectrophotometers and viscometers, to measure these properties with precision. Any deviations from the desired specifications are identified and corrected before the product moves to the packaging stage. Packaging is the final step in the production process, and it plays a critical role in preserving the freshness and quality of the cocoa powder. The powder is first sifted to remove any clumps or oversized particles, ensuring a uniform texture. It is then transferred to automated filling machines, which dispense precise amounts of cocoa powder into containers such as tins, pouches, or bulk bags. For retail packaging, the containers are often flushed with nitrogen gas before sealing to remove oxygen and prevent spoilage. Labels are applied to the packages, including information such as the brand, product type, lot number, and expiration date. Once packaged, the cocoa powder undergoes a final round of inspections, where advanced vision systems check for defects such as improper sealing, misaligned labels, or damaged containers. The finished products are then packed into cartons or cases using robotic packaging systems. Palletizing robots stack the cartons neatly onto pallets, which are shrink-wrapped for stability and loaded onto trucks or shipping containers for distribution. The production of Domino's pizza begins not in the store kitchens, but in massive regional supply chain centers, where the ingredients, particularly the dough, are produced in industrial quantities with an emphasis on consistency, quality, and efficiency. Before any pizza reaches the oven in a Domino's franchise, it starts its journey in these highly controlled factory environments, where each element is formulated to exact specifications. The first and most critical component is the dough, which is made fresh daily in these centers and delivered under cold storage conditions to every Domino's outlet. The dough making process begins with the arrival of bulk ingredients, including high-protein wheat flour, water, vegetable oil, yeast, sugar, and salt. These ingredients are stored in separate storage systems based on their physical state and volume requirements. Flour is kept in massive silos connected to the production floor through pneumatic tubing systems. These tubes transfer flour directly into the industrial-scale mixers with precise weight measurements, controlled by automated batching systems. Water, which must be maintained at a specific temperature range to activate the yeast properly, is stored in stainless steel tanks connected to digital flow meters. This ensures the exact volume is dispensed into each batch, typically to within 1/10 of a liter. Vegetable oil, sugar, salt, and yeast are also dispensed through closed-loop systems that prevent contamination while ensuring high-speed delivery and accuracy. The industrial mixers used at this stage are horizontal, high-capacity spiral mixers or fork mixers, depending on the location and the specific equipment model in use. Each mixer is designed to handle hundreds of pounds of dough per batch, usually around 400 to 600 pounds. The process begins with dry ingredients being added first, followed by a controlled stream of water and oil. Once the mixture reaches the desired hydration point, the mixer operates at different programmed speeds to knead the dough until it reaches the correct elasticity and gluten development. This usually takes around 8 to 10 minutes, with temperature sensors embedded in the bowl to prevent overheating from friction, which can damage the yeast. As the dough mixes, factory floor operators monitor each batch's time, temperature, and consistency through a computerized interface. Every mixer is part of a larger manufacturing execution system that records batch data, ingredient lots, timestamps, and operator IDs. This traceability system ensures that if a problem ever arises, such as inconsistent rise or poor texture in a batch, managers can track it back to the specific flour lot or mixing time and make necessary adjustments for future runs. Once the dough reaches optimal consistency, it is automatically discharged from the mixer into a dough trough, which is essentially a wheeled stainless steel container that holds the dough until it's moved to the dividing station. The dough is then transferred into a hopper above a hydraulic or rotary dough divider. This machine uses either vacuum-assisted suction or mechanical cutting blades to portion the dough into uniformly weighted balls, typically ranging from 6 to 20 ounces, depending on the final pizza size. Each portion is measured by load cells, digital weighing systems that maintain accuracy within a few grams. These dough balls then proceed to the rounding machine, which takes each divided piece and rolls it into a tight, smooth sphere. This is crucial for creating the internal tension needed for a uniform rise during fermentation. The rounding machine uses rotating plates or belts that apply gentle pressure and a circular motion to the dough. After rounding, the dough balls are dusted lightly with food-grade flour or semolina to prevent sticking, and then placed into oiled dough trays. These trays are stacked and covered with plastic lids or wraps to maintain humidity and prevent surface drying. They're labeled with a printed barcode that includes the production date, time, dough type, and batch number. At this point, the dough enters the proofing phase, which is critical to developing both the structure and flavor of the final pizza base. Proofing occurs in temperature and humidity-controlled rooms, where racks of dough trays are stored for several hours. The ideal proofing conditions are generally around 80 degrees Fahrenheit with 75% relative humidity, although this can vary slightly based on factory location and yeast activity. The yeast begins to consume the sugars in the dough, producing carbon dioxide and ethanol as byproducts. This gas becomes trapped within the dough's gluten network, causing it to expand and develop the characteristic airy, chewy structure. Simultaneously, organic acids and alcohols created during fermentation start to build complex flavor notes in the dough. During the proofing period, plant operators conduct regular checks to monitor dough expansion, surface tension, and even internal temperature using infrared thermometers and visual inspection. Some factories use automated camera systems that scan the trays and calculate proofing progress by measuring the dough's rise and dome shape. Any deviations from the standard profile are flagged for intervention, whether that means extending the proofing time or moving certain trays to a different section of the proofing room. Once the dough reaches the desired level of fermentation, it is moved to the cold storage phase. In this stage, the dough trays are rolled into large walk-in refrigeration rooms, where the temperature is maintained at approximately 2 to 4 degrees Celsius. This halts the yeast's activity and locks in the developed flavor while also preventing overproofing. The chilled dough can now be stored for up to several days, depending on demand at the destination stores. During this time, the trays are rotated to maintain even cooling and are occasionally inspected for signs of over-fermentation or drying. While the dough is being prepared, Domino's is also handling the sauce production in parallel. Tomato sauce is made in separate processing areas, using high-volume stainless steel kettles equipped with agitators and heating jackets. The base of the sauce is tomato paste, which is diluted with water to reach a specific consistency. To this, measured quantities of salt, sugar, oregano, garlic, basil, black pepper, and other proprietary spices are added. Some locations use pre-mixed spice sachets that are batch-coded for accuracy, while others blend the seasoning on-site. The sauce mixture is heated to temperatures between 80 and 90 degrees Celsius to sterilize it and meld the flavors. Once the heating process is complete, it is rapidly cooled using a plate heat exchanger to bring it down to refrigerated storage temperature, usually 30 degrees Celsius, around 4 degrees Celsius. The cooled sauce is then transferred into food-safe storage containers, often in 10-liter or 20-liter units, and sealed with tamper-evident caps. Each container is labeled with a batch code and production date before being staged for shipment alongside the dough. In addition to sauce, the factory prepares other key ingredients, including shredded cheese and select toppings. The cheese used in Domino's pizzas is typically a low-moisture mozzarella, known for its excellent melting properties and stretch. Some supply centers receive the cheese in bulk blocks and shred it in-house using high-speed rotary shredders that slice the blocks into uniform strands. The shredding process includes a light coating of anti-caking agents like potato starch or cellulose to prevent clumping during storage. The shredded cheese is packed into portioned bags, vacuum sealed, and stored under refrigeration. Once all ingredients, dough, sauce, cheese, and prepped toppings are ready, they are organized and loaded into refrigerated delivery trucks. These trucks operate under a tight logistics schedule, making daily or multi-day trips depending on the volume needs of each Domino's franchise store. The internal temperature of each truck is continuously monitored using GPS-integrated data loggers, and real-time data is fed back to the supply center's central operation system. This ensures that if any deviation in temperature or route timing occurs, corrective action can be taken immediately. By the time the products arrive at the store, they are fully prepared and only require assembly and baking. The franchise stores then execute the final steps of pizza preparation, which involves pressing out the dough, saucing, topping, baking, and packaging. However, the factory's role is absolutely central to ensuring that every ingredient arrives at the exact same standard, no matter where the pizza is being made or consumed. Through this centralized and automated model, Domino's achieves consistency at a global scale, while minimizing waste and human error in the earliest and most foundational stages of production. Once the refrigerated trucks deliver the dough, sauce, cheese, and toppings to each Domino's franchise, the handling of those ingredients transitions from centralized factory production to carefully structured in-store processes that continue to follow standardized protocols. However, the factory's influence is far from over at this point. The store-level procedures are engineered to mirror the consistency, precision, and speed found in the supply chain centers, effectively extending the factory environment into each retail location. Inside the store, the first critical action is the proper storage of the dough. As the dough trays arrive straight from cold storage, they are transferred into the store's walk-in refrigerator, where they are kept at a consistent temperature of 2 to 4 degrees Celsius. Each dough tray remains sealed with its identifying barcode, which includes the production batch, date, and shelf life. This code is scanned upon arrival, logged into the store's inventory system, and linked to the store's daily forecast so the staff can prioritize older dough for earlier use, following a strict first in, first out system to ensure freshness and prevent waste. Before the dough can be used for making pizzas, it needs to temper. Cold dough straight from refrigeration is too stiff and contracted to stretch evenly or bake correctly. Therefore, several trays are pulled from the cooler in staggered intervals and placed in a proofing area within the store, typically kept at room temperature for 30 to 60 minutes. During this period, the dough relaxes, allowing the gluten to become more extensible and the yeast to reawaken slightly, which enhances browning and flavor development in the oven. This step also restores some of the softness and elasticity necessary for the dough to perform consistently on the preparation line. The next key phase in the process is dough pressing or hand stretching, which transforms the proofed dough ball into a pizza base. Depending on the store's equipment and regional preferences, Domino's uses one of several standard methods for this. In many high-volume locations, a mechanical dough press is employed. This press is a heated platen system where a single dough ball is centered between two metal plates. With controlled pressure and temperature, the plates compress the dough to the specified diameter and thickness. The brief heat exposure also helps to set the edge of the crust slightly, which prevents overexpansion during baking. Other stores use hand stretching techniques, which involve manually flattening the dough using the palms and fingertips to create an even disc, often followed by a gentle spinning motion to widen it to the correct diameter. Employees are trained to feel for even dough resistance, check the uniformity of thickness, and ensure the edges are slightly thicker to create the signature Domino's crust ring. Some locations employ a dough sheeter, a machine that flattens dough between two adjustable rollers, which is commonly used for medium thickness crusts or thin crust options. Once the dough is properly shaped and placed on a pizza screen or baking tray, it is ready to be sauced. The sauce comes in pre-measured containers or large bag-in-box systems with pump dispensers, depending on the store's volume. A standardized rotary sauce ladle or domed saucer is used to apply a precise amount of sauce, usually between 90 and 120 grams for a medium pizza. The sauce is spread using a circular motion that stops approximately 1 inch from the crust edge to allow for natural bubbling and rim development during baking. With the base sauced, the next step is the cheese application. Domino's cheese is a proprietary, low-moisture mozzarella blend, optimized for melt, stretch, and browning. The cheese arrives shredded in sealed, chilled bags and is stored in under-counter refrigeration near the prep stations for quick access. Employees use color-coded scoops to portion out exact grams of cheese per pizza size: small, medium, large, or extra large. This consistency ensures that the cheese melts evenly and that the nutritional and caloric values remain standardized. In high-throughput stores, preloaded portion dispensers or weigh scales may also be integrated into the cheese station to reduce time and improve accuracy. Next, the pizza moves to the topping stage. Domino's toppings, such as pepperoni, Italian sausage, mushrooms, green peppers, onions, olives, jalapenos, grilled chicken, and bacon, are kept in ingredient rails with stainless steel pans, maintained at safe refrigeration temperatures using undermounted chillers. Each topping has a designated scoop or set of tongs, and employees are trained to apply the correct amount and distribution per pizza size and recipe. Toppings are applied in a set sequence to ensure even cooking and consistent flavor layering. For example, pepperoni slices are laid edge to edge to cover the surface in a signature circular pattern, while sausage crumbles are more scattered to allow airflow between pieces. Vegetables are typically added last, as their moisture content can impact the crispness of the crust if layered too deeply. Domino's uses laminated guides and portion charts to ensure that every pizza, regardless of who's preparing it, looks, weighs, and tastes the same. With the pizza fully assembled, it is placed onto a conveyor belt oven, also known as an impingement oven. This oven style uses jets of superheated air blasted from top and bottom to ensure even baking. The oven belt is set to a precise speed, generally resulting in a 5.5 to 7 minute bake time, depending on the pizza size and topping density. The oven's digital interface allows staff to select different profiles for thin crust, hand-tossed, deep dish, or extra cheese options. Each profile adjusts air velocity, top and bottom heat ratio, and belt speed to produce the ideal bake for that style of pizza. During baking, several chemical and physical transformations take place. The crust expands slightly from the final stage of yeast fermentation. Steam is released from the sauce and toppings, and the cheese melts and begins to brown through the Maillard reaction. Excess moisture from vegetables is evaporated by the oven's airflow, ensuring the crust remains crisp and doesn't sag. The pizza emerges from the other side of the oven, fully baked and ready for slicing. At the end of the conveyor, pizzas are transferred to a staging counter, where they rest for 20 to 30 seconds to allow the cheese to set slightly. Then, using a rocker blade or circular pizza cutter, employees cut the pizza into standard portions, usually 8 slices for a large pizza, based on Domino's cutting guides. Each pizza is then slid into a branded corrugated cardboard box, which is specially designed with vent holes and moisture-absorbing liners to preserve crispness during delivery. Every box is sealed and receives a printed label generated by the store's order management system. This label includes the customer's name, order number, timestamp, and pizza specifications. For orders placed online or through the app, this also triggers an update on Domino's proprietary pizza tracker, which uses real-time data from kitchen sensors to notify customers of each stage, from dough prep to oven entry, baking, boxing, and out for delivery status. Throughout the day, all these processes are monitored for compliance with Domino's global standards. District managers conduct regular audits using detailed checklists covering dough handling, oven cleanliness, bake quality, topping accuracy, and safety procedures. Additionally, Domino's has built-in kitchen timers and alert systems that ensure no dough is held at room temperature too long, no pizzas sit unboxed beyond the quality threshold, and no ingredients are used past their hold times. Each store's operations are built to match the precision and consistency of the supply chain factories. In fact, many stores undergo periodic retraining sessions to realign their practices with the upstream factory procedures. This ensures that no matter how far the finished product is from the centralized dough production, the final experience to the consumer remains nearly indistinguishable between one location and the next. As soon as a Domino's pizza is sliced and boxed, the journey continues into a carefully engineered phase focused on preserving product quality and maximizing delivery efficiency. At this point, what might appear to the customer as the simple act of putting a pizza in a box and sending it out the door is, in reality, a continuation of Domino's factory-grade systems, refined, tracked, and executed with industrial precision. Each Domino's box is made of specially designed corrugated cardboard, engineered not only to be structurally strong enough for stacking and transportation, but also to allow moisture control and thermal retention. Small vent holes are strategically placed around the box edges to allow steam to escape without sacrificing internal heat. This is critical to maintaining a crisp bottom crust while keeping the cheese and toppings hot and intact during transit. The liners inside some specialty pizza boxes also use grease-resistant coating and moisture-wicking micro layers that reduce sogginess, especially in pizzas with heavier vegetable or meat toppings. Once the pizza is placed in its box, a label is immediately printed and applied. This label contains all relevant details: the order number, pizza type, time of bake, the customer's name and address, and specific cooking instructions if applicable, like extra crispy crust, light sauce, or no cheese. More importantly, the label also includes digital timestamps and batch codes that tie the finished product directly back to every earlier phase of production. These codes link the order to its dough batch, sauce mix, cheese lot, and even the name of the employee who boxed it. This allows full traceability, and in the event of a customer complaint or quality issue, managers can pull up detailed records to investigate and resolve the problem efficiently. The next link in the process is the delivery system, which Domino's has industrialized to a level similar to its supply chain and production operations. Every Domino's location uses a centralized digital system to optimize delivery routes, monitor driver location, and track pizza temperature using estimated time-to-door algorithms. In some urban areas or flagship locations, Domino's even uses thermal sensors and GPS modules in the delivery bags themselves. These sensors ensure that the pizza never drops below the acceptable temperature threshold, typically around 140 degrees Fahrenheit or 60 degrees Celsius, which maintains cheese integrity and topping stability. The delivery bags used are not basic insulated containers. They are purpose-built thermal sleeves with advanced insulation material, sometimes incorporating phase change materials that hold heat without overheating the product. These bags are lined with aluminum and closed with Velcro or zippers to ensure no heat escape. In some pilot programs, Domino's has experimented with electrically heated delivery pouches that plug into the vehicle's charging outlet maintaining a regulated temperature across the entire delivery window, especially in colder climates. While the pizza is en route, Domino's proprietary pizza tracker remains active. This cloud-based interface receives inputs from multiple sources: the POS system, kitchen sensors, label printer, and delivery dispatch terminal, and creates real-time updates for the customer. As soon as the order is marked out for delivery, a countdown begins based on predictive delivery timing, factoring in distance, time of day, historical traffic data, and driver availability. This transparency not only improves customer satisfaction, but also provides performance data for internal use. Behind the scenes, Domino's aggregates all this operational data into their enterprise-wide performance dashboards. Each store's key performance indicators, such as order accuracy, delivery time, baking efficiency, and customer satisfaction scores, are updated daily. Store managers and regional supervisors review these metrics in regular meetings, identifying trends, deviations, and opportunities for improvement. If a certain franchise location consistently shows slower bake times or increased complaints about cold pizza, it may trigger a maintenance review of the oven system or retraining of kitchen staff. Meanwhile, at the supply chain level, Domino's uses reverse logistics to complete the factory-style loop. Once a delivery is completed, used ingredient bins, dough trays, and empty sauce containers are returned to the regional supply centers on the next inbound truck trip. These items are cleaned, sanitized, and reused according to food safety protocols. Reusable dough trays, for example, go through automated washing systems that use high-pressure jets, detergent, and thermal sanitation to prepare them for the next production cycle. By managing both outgoing and incoming flows efficiently, Domino's minimizes waste and maximizes logistical efficiency, keeping the system sustainable and cost-effective. Beyond the visible kitchen and delivery operations, there is also a sophisticated forecasting and inventory management system that relies heavily on factory data. Using AI and machine learning, Domino's forecasts demand for dough, sauce, cheese, and toppings at each store based on variables like local events, weather, historical order volumes, and even social media trends. This information is transmitted back to the supply chain centers, which adjust dough production and ingredient packaging accordingly. For example, if a city is expecting a snowstorm, the system may predict a spike in delivery orders and increase dough production by 10% for the affected stores. This tight integration between forecasting and factory production minimizes spoilage and overproduction, ensuring that only as much dough and sauce is produced as will be used within a defined freshness window. The same logic applies to toppings and cheese. Ingredients that are nearing the end of their shelf life can be flagged automatically, prompting store managers to run promotional offers or bundle deals to encourage faster turnover. By linking the retail environment back to the factory floor, Domino's achieves a level of responsiveness and precision rarely seen in traditional food service operations. Domino's also incorporates periodic updates and R&D feedback into its manufacturing systems. When a new product is launched, such as a specialty crust or a new line of toppings, the manufacturing centers adapt their formulations and packaging processes to accommodate the change. For instance, a new crust option may require a dough with a different hydration level or proofing profile. In that case, dough mixers are recalibrated, proofing room settings adjusted, and additional QA steps introduced. The product launch timeline includes upstream changes that affect every supply chain center, down to the labeling system and transport logistics. To maintain global brand consistency, Domino's has standardized its production protocols across all countries, yet also incorporates regional customization. For instance, the dough produced in India may include slight formulation changes to better suit local humidity levels or flour types. In Japan, where crust styles vary, dough mixing and resting procedures may be adapted for fluffier or rice-infused bases. However, the core manufacturing principles, precise batching, automated mixing, cold chain delivery, and digital inventory tracking, remain consistent regardless of geography. Domino's also performs routine auditing and calibration of their supply chain centers to ensure continued alignment with performance standards. Factory equipment such as mixers, dividers, and temperature control units are subjected to preventive maintenance and calibration checks at regular intervals. Technicians verify dough density, elasticity, and yeast activity using physical measurements and digital readouts. Similar checks are done for sauce viscosity, cheese fat content, and topping moisture levels. These numbers are logged and analyzed to identify any drift from target specifications, allowing corrective measures to be implemented before product quality is affected. Even packaging materials go through quality control. Corrugated boxes are tested for burst strength, fold endurance, and thermal retention properties. Adhesives used for box sealing are food safe and resistant to temperature extremes. The printing quality on labels is monitored to ensure clarity and durability, as these labels serve both customer-facing and internal traceability functions. Everything down to the ink used on packaging is selected for durability under heat and moisture, a testament to the factory-level thinking that permeates the entire Domino's ecosystem. Industrial sugar production begins with harvesting, and depending on the region and facility specialization, the factory will receive either sugarcane or sugar beets. These two crops require distinct processes to extract sucrose, though many of the underlying steps, washing, crushing, juice clarification, and concentration, are similar in principle but differ in machinery, timing, and chemical inputs. Let's start with sugarcane. Sugarcane is a tall, fibrous grass grown in warm, tropical climates. It is harvested either manually, using machetes, or mechanically using harvesters that cut the stalks and strip the leaves in a single pass. Once cut, the cane begins degrading immediately, so it must be delivered to the processing facility quickly, typically within 24 to 48 hours, to preserve sucrose content and prevent microbial activity that would convert sugar into acids. The cane arrives at the factory by truck and is offloaded into massive intake yards. These yards are equipped with cranes or grab loaders that lift entire truckloads of cane and dump them onto conveyors that feed the primary cleaning line. Before any juice can be extracted, the cane must be washed to remove soil, leaves, and insects. This is accomplished with a combination of rotating drum washers and high-pressure spray systems that bathe the stalks in recycled processed water. The water itself is filtered and reused in a closed-loop system to reduce environmental impact. Once clean, the cane is conveyed to a chopper station. Here, high-speed rotating blades slice the cane into short sections to expose the inner fibrous material. The chopped cane then moves through a shredder, a powerful hammer mill type machine that tears the cane into finer particles. This dramatically increases the surface area of the plant material, making the sugar easier to extract in the next stage, milling. The shredded cane is now ready for juice extraction via mechanical milling. This takes place in a series of large, heavy-duty roller mills, typically arranged in a tandem line of 5 to 7 stations. Each station consists of 3 rollers, 2 lower and 1 upper, that compress the cane with immense pressure. As the cane passes through each station, more juice is squeezed out. Water is sometimes sprayed onto the crushed cane, a process called imbibition, to help wash out more sucrose during the final passes. The resulting juice, known as mixed juice, is a cloudy, pale green liquid that contains not just sucrose, but also fibers, proteins, organic acids, and soil particles. What remains of the cane after this process is a dry, fibrous residue known as bagasse. Rather than being discarded, bagasse is transported to a boiler house where it is burned as fuel to generate steam and electricity for the plant itself, often making the facility energy self-sufficient. Meanwhile, the mixed juice moves to the clarification phase. Before sucrose can be crystallized, impurities need to be removed. The first step is heating. The juice is pumped through a series of shell and tube heat exchangers to bring it up to around 105 degrees Celsius. This temperature helps precipitate some of the colloidal particles and also prepares the juice for chemical treatment. In the next stage, the juice is sent to a reaction tank where lime, typically calcium hydroxide, is added. This raises the pH of the juice and helps neutralize acids, precipitate proteins, and coagulate other impurities. The exact dosage of lime is tightly controlled using inline pH meters and flow-regulated injection systems. Flocculants may also be added at this stage to help bind the fine particles into larger clumps. After chemical treatment, the juice enters a clarifier, a large settling tank where gravity separates the solids from the liquid. The solids, known as mud, settle to the bottom and are periodically removed through rotary scrapers and pumped to a filter press where the water content is removed. The resulting cake is either composted or used as a soil amendment. The clarified juice, now a light amber color and much cleaner, is drawn off from the top of the clarifier and sent to the next phase, evaporation. Let's now consider the sugar beet process, which starts quite differently. Sugar beets are harvested using machines that dig them from the soil and remove most of the leaves and dirt. At the factory, the beets are washed in flumes, long channels of water that carry the beets through a series of mechanical washers and screens. Stones and heavy debris are removed using density separation, while fine silt is filtered out with mesh drums and hydrocyclones. Once clean, the beets are sliced into thin strips called cossettes. These are fed into a diffuser, a long vertical or horizontal tank where hot water is sprayed over the beet slices. The water temperature is controlled to around 70 degrees Celsius and flows countercurrent to the beet material, maximizing sugar extraction. The sugar diffuses from the plant cells into the water, forming raw beet juice. This juice is then pumped to its own clarification stage, where lime and carbon dioxide are used in a process called carbonation. Calcium carbonate forms during the reaction and binds impurities, which are then filtered out, leaving behind a clarified beet juice ready for concentration. Both the cane and beet clarification processes converge at this point. They now have a clean, thin juice rich in dissolved sucrose. The next step in both methods is evaporation, which we'll explore in full detail in the following section. But for now, we've completed the complex, high-volume, highly monitored beginning of sugar manufacturing, where plant material is transformed, filtered, and chemically prepared for crystallization. Every moment of this phase is controlled with real-time feedback systems, mechanical separation equipment, and chemical treatments that must be perfectly balanced to set the stage for pure, white sugar to eventually take form. With the clarified juice now prepared, whether from sugarcane or sugar beets, the next major operation in industrial sugar production begins: evaporation. This process is designed to concentrate the diluted juice, which at this stage contains roughly 12 to 16% sucrose by weight, into a thick syrup known as thick juice or syrup, with a sucrose content of about 60 to 70%. The transition from thin juice to syrup is achieved by removing most of the water through a carefully staged thermal process. This concentration step is not just about volume reduction, it also creates the right conditions for crystallization to occur later with control and precision. Evaporation in a sugar factory is typically carried out using a multi-effect evaporator system. These systems are composed of 5 to 6 large vertical vessels, known as effects, connected in series. Each effect operates at a slightly lower pressure than the one before it. allowing the juice to boil at progressively lower temperatures. This setup significantly improves energy efficiency. Steam generated in one effect is reused to heat the next, conserving thermal energy throughout the process. The clarified juice enters the first effect and is heated with steam to just above its boiling point, typically around 115 degrees Celsius. As the juice boils, water vapor is released and rises to the top of the vessel, while the increasingly concentrated juice remains below. The steam from this first vessel is then routed into the heating coils of the second effect, where it causes the juice in that chamber to boil at a slightly lower temperature due to its reduced pressure. This cascading effect continues through all stages, progressively concentrating the juice without requiring additional high-pressure steam inputs at each stage. Throughout this process, automated sensors track the Brix value, sugar concentration, temperature, and pressure in each vessel. Flow controllers and level sensors regulate how much juice is transferred from one effect to the next, ensuring consistent residence time and thermal exposure. Operators monitor these values from a centralized control panel equipped with real-time displays and alarms. If any chamber's temperature deviates beyond acceptable limits, the system automatically adjusts steam input or juice flow to compensate. By the time the juice exits the final effect, it has thickened into a dense, amber-colored syrup with a viscosity similar to honey. It now contains upwards of 65% sucrose and has a reduced water activity, which helps to stabilize it against microbial spoilage. At this point, it's ready to enter the crystallization phase, a controlled process designed to coax sucrose molecules out of solution and into solid form. Crystallization begins in large, jacketed vacuum pans. These are vertical, cylindrical vessels where the thick syrup is further boiled under vacuum to lower the boiling point and prevent caramelization or degradation of the sugar. Reducing pressure allows boiling at temperatures around 60 to 70 degrees Celsius, preserving product quality. Inside each pan, agitators or stirrers keep the syrup moving, while high surface area heating coils provide uniform thermal input. The process begins with the introduction of a small amount of fine sugar crystals, called seed crystals or slurry. These seeds serve as nucleation sites around which sucrose molecules begin to gather and grow. The timing and uniformity of seeding are crucial. If seeded too early, too many crystals form, resulting in fine-grained sugar. If done too late, oversized or irregular crystals can result, affecting yield and downstream processing. Once seeded, the vacuum pan is held at a steady boil, and the syrup is gradually fed into the vessel in a process known as strike feeding. As more syrup enters, the crystals continue to grow while the water content is simultaneously reduced by evaporation. Operators closely watch the strike through sight glasses or by withdrawing small samples to examine crystal size and consistency under polarized light. When the desired crystal size and saturation level are reached, the strike is dropped, transferred to a large horizontal vessel called a crystallizer. Here, the mass, now called massacute, is gently stirred and cooled over several hours to allow further crystal growth and uniformity. The goal is to achieve maximum recovery of sucrose in solid form, leaving behind a thick mother liquor known as molasses. Once cooled and matured, the massacute is ready for centrifugal separation. Industrial sugar centrifuges are large, high-speed machines with perforated baskets that spin at up to 1,200 revolutions per minute. When the massacute is loaded into the centrifuge, the force of spinning flings the liquid molasses through the perforations, while the denser sugar crystals remain behind. Water or steam is sprayed onto the sugar during spinning to remove any residual molasses and improve crystal brightness. After spinning, the raw sugar is discharged from the centrifuge as damp, tan-colored granules. If the plant's end product is raw sugar, for example, in a raw cane sugar mill, This product is conveyed to dryers and then bagged or bulk loaded for transport to a separate refinery. However, in a full refining operation or beet sugar plant, further purification steps are carried out to produce white, food-grade refined sugar. The raw sugar is sent to a melter where it is dissolved in hot water to form a clear sugar liquor. This liquor undergoes multiple filtration steps, including activated carbon treatment and phosphatation or carbonatation, depending on the process. These methods remove colorants, organic compounds, and trace minerals. In the case of carbonatation, lime and carbon dioxide are added to form calcium carbonate, which binds impurities and is filtered out. After decolorization and final filtration, the sugar liquor is sent through a second crystallization stage, nearly identical to the one used for raw sugar, but this time targeting higher purity and clarity. The white sugar crystals formed in this process are sharper, brighter, and finer than raw sugar and are typically centrifuged, washed, and dried in a fluidized bed dryer. This dryer suspends the crystals on a bed of warm air that circulates through the granules, gently removing moisture without breaking the crystals. The final product is pure, white granulated sugar with a typical purity of 99.9% sucrose. It is cooled to ambient temperature and stored in silos constructed of stainless steel or food-grade plastic, protected from moisture and pests. These silos are equipped with temperature and humidity sensors, along with vibrating floors or fluidizing systems to prevent caking or compaction during long-term storage. From here, sugar can be packed into a wide variety of formats: retail-sized paper bags, industrial bulk sacks, or even liquid sugar totes, depending on customer requirements. All packaging is done in cleanroom grade conditions, using automated lines that fill, weigh, seal, and label each unit with production codes and batch tracking information. So far, we've followed the process from raw juice to pure sugar, navigating evaporation, crystallization, centrifugation, and drying. The next segment will explore how factories handle byproducts like molasses, manage energy usage with bagasse or beet pulp, and maintain food safety, quality assurance, and environmental compliance throughout continuous 24/7 operations. Now that the core crystallization and drying stages of sugar manufacturing have produced refined, food-grade white sugar, the final phases of the industrial process turn to three key pillars: byproduct management, energy and sustainability practices, and rigorous quality control systems that ensure every grain of sugar meets the specifications for purity, safety, and consistency. Modern sugar factories are not only high-output food production plants, they are also vertically integrated resource management systems designed to handle waste, generate energy, and produce multiple co-products with commercial value. Let's begin with molasses. After the centrifugation stage, once sugar crystals have been separated from the remaining syrup, what's left behind is a dense, dark, viscous liquid, molasses. This mother liquor still contains residual sucrose along with glucose, fructose, organic acids, minerals, and other non-crystallizable solids. The amount and composition of molasses can vary based on the raw material, cane or beet, the efficiency of crystallization, and the desired yield of refined sugar. In cane sugar operations, molasses is often drawn off after the second or third crystallization strike. Rather than being discarded, it's routed to molasses storage tanks, where it is either sold as a feedstock for ethanol distilleries or used as livestock feed due to its high energy and nutrient content. In some facilities, molasses is further processed to extract minor quantities of sugar through high-efficiency ion exchange or chromatographic separation, but this is only economically viable at large scale, or where sugar recovery is subsidized. In beet sugar production, molasses has a different profile, slightly lower in fermentable sugars, but rich in betaine and other organic compounds. It is also collected in holding tanks and transported in heated tanker trucks to fermentation plants, where it can be used in the production of yeast, citric acid, or industrial ethanol. In all cases, the molasses is handled under strict hygienic conditions to prevent spoilage or microbial contamination. Another major byproduct of sugar processing is bagasse, the fibrous, woody material left over from crushing sugarcane stalks. Rather than treating it as waste, factories utilize bagasse as a biofuel. It is burned in high-pressure boilers to generate steam, which is then used to power turbines that produce electricity for the entire sugar mill. Many sugar plants operate as self-sufficient cogeneration facilities, producing not only enough power for internal use, but also exporting surplus energy to nearby grids. Bagasse combustion systems are outfitted with flue gas scrubbers, electrostatic precipitators, and ash management systems to minimize air emissions and collect residual ash. This ash, in turn, may be used in agriculture as a soil amendment due to its mineral content, or it may be mixed with other waste materials to create compressed fuel briquettes. Some advanced mills pelletize dried bagasse for sale to industrial burners or biomass energy producers. Beet processing also generates fibrous residues, known as pulp. After the sugar has been extracted in diffusers, the beet pulp is pressed to remove excess moisture and then sent to drying systems, usually rotary drum dryers or flash dryers. The resulting dried beet pulp is then either pelleted or ground into flakes and sold as animal feed, particularly for cattle. High in fiber and moderately sweet, beet pulp is valued in the livestock industry for both energy and palatability. In both beet and cane facilities, the wastewater generated during washing, evaporation, and cleaning operations must be treated before discharge. Factories operate full-scale wastewater treatment plants that include sedimentation tanks, anaerobic and aerobic digesters, pH correction units, and sometimes membrane filtration. These systems are monitored continuously using turbidity sensors, chemical oxygen demand (COD) analyzers, and automated flow controllers. In some operations, treated effluent is reused internally for irrigation, ash quenching, or process water, further reducing the factory's environmental footprint. Solid waste is minimized through integrated process design. Soil and rocks from beet or cane washing are separated and sent to land reclamation or construction material applications. Boiler ash, as mentioned earlier, is either reused or compacted and safely landfilled. Filter cake from juice clarification, rich in organic matter and lime, is collected and sold as fertilizer, particularly in regions where soil pH management is important for crop health. Alongside waste handling and energy management, quality control is one of the most sophisticated systems operating inside a sugar plant. From raw material to final product, multiple checkpoints are established to measure, record, and verify key parameters. Quality assurance starts with raw material sampling. Upon arrival, cane or beets are tested for sucrose content, fiber, moisture, and purity. These values inform process adjustments and predict yield per ton of raw input. In the evaporation stage, bricks, soluble solids content, is measured at every effect using inline refractometers. These instruments use light refraction to instantly calculate sugar concentration in real time. Operators can adjust feed rates, heating input, or flow pressure based on these readings to maintain target consistency. During crystallization, samples are withdrawn at set intervals and examined under microscopes for crystal shape, size distribution, and purity. Technicians monitor the color using ICUMSA, International Commission for Uniform Methods of Sugar Analysis, standards, with high purity white sugar scoring under 45 ICUMSA units. If color values trend too high, indicating the presence of residual molasses, operators can make real-time adjustments to seeding rates or massacute concentration. After drying and cooling, Sugar samples are run through particle size analyzers and moisture content meters. The particle size must fall within strict specifications depending on the final use. Granulated table sugar, for instance, has tighter specs than coarse industrial sugar destined for beverages or confections. Moisture content is typically targeted below 0.05% to ensure long shelf life and prevent clumping. Final color, purity, and turbidity tests are logged digitally and associated with specific batch codes for traceability. Packaged sugar is subjected to additional inspection. Bags, sacks, or containers are weighed using high-speed check weighers that verify fill accuracy to within plus or minus 0.2% of the labeled net weight. Vision systems inspect print clarity, barcode legibility, and seam integrity. Packages that fail any of these checks are diverted and manually reviewed. Silos storing finished sugar are equipped with real-time inventory monitoring systems using load cells and level sensors. Temperature and humidity are also monitored to prevent caking or condensation. In some regions, silos are also flushed with dry, filtered air to reduce microbial risk in high humidity climates. Across the plant, digital SCADA systems pull data from all production stages. Operators view real-time dashboards showing flow rates, temperature curves, impurity removal efficiency, and steam usage. These systems not only ensure daily operational control, but also provide long-term analytics for performance improvement. Advanced factories even deploy machine learning tools that analyze historical data to predict maintenance needs or recommend minor adjustments to maximize recovery rate and minimize energy consumption. To comply with food safety and export standards, many sugar factories operate under ISO 22000, FSSC 22000, or BRCGS certifications. This requires documented hazard analyses, allergen control programs, cleaning protocols, and traceability audits. Every production lot is labeled with a batch ID that connects back to a full production record: raw input, processing conditions, lab results, and packaging date. Customer-specific requirements are also programmed into the system. For example, pharmaceutical-grade sugar used in oral medications must meet even higher purity and microbial specifications, and may be filtered again through fine mesh screens and sterilized using UV or ozone treatments before final packaging. In some cases, sugar is converted into liquid form, known as liquid sucrose or invert sugar, by dissolving granulated sugar in heated, purified water, and, in the case of invert, breaking down sucrose into glucose and fructose using acid or enzymatic hydrolysis. These liquid sugars are pumped into sterile tankers or IBCs, intermediate bulk containers, and shipped under temperature-controlled conditions to manufacturers in the beverage, dairy, or baked goods industries. Even at this late stage, the role of the sugar factory is far from static. Engineers continue monitoring consumption trends, regulatory shifts on added sugars, and regional demand to adjust capacity and format offerings. New packaging materials, biodegradable options, and energy recovery systems are constantly being evaluated and trialed, keeping the entire facility in a state of adaptive optimization. With refined sugar now stored in silos, bulk bins, or sterile containers, depending on its intended form, the focus turns to distribution, packaging, and how this versatile ingredient is tailored to the requirements of a wide array of customers, from retail consumers to massive industrial clients. This final stage is no less complex than the upstream processing phases. In fact, it involves its own dedicated systems for handling, labeling, traceability, and product customization. At this point in the factory, packaging lines diverge into three main pathways: consumer packaging, industrial bulk packaging, and liquid sugar dispatch. Each line is specifically engineered for its product format. and all are equipped with high-speed automation and real-time quality assurance systems. For retail products, such as granulated white sugar sold in 1 kilogram or 2-pound paper bags, the packaging line begins by feeding dry sugar through a vibratory chute into a vertical form-fill seal machine. The sugar passes through a flow meter and enters a funnel that drops it into a preformed bag made from food-grade paper or composite film. These bags are formed, filled, and sealed in one continuous motion. The machine prints batch numbers, expiration dates, and sometimes QR codes or traceability data on each bag. Each filled package passes through a metal detector and X-ray scanner to ensure that no foreign objects are present. Then, check weighers confirm that the net content is accurate within a narrow margin. Any under or overweight packages are automatically rejected and flagged for operator review. The approved bags are collected into bundles, often shrink-wrapped into 10 packs, and sent to palletizers that stack them for warehouse distribution. For industrial customers, packaging formats differ significantly. Sugar may be packed into 25 kilogram woven polypropylene bags, 50 kilogram sacks, or even 1-ton bulk bags called FIBCs, flexible intermediate bulk containers. These bags are filled using gravity-fed hoppers mounted on load cells that ensure weight accuracy.